Today we have session from 9 a.m. We are delayed by nearly 10 minutes now, and for the first session, Professor David Field will be talking about fundamentals of triple junctions and importance of nanostructured polycrystal. It might be a little bit of different topic, but it will be more or less same. Then Professor Devalaya Chakrabarty from 10 a.m. Then Professor Sumantra Mandal. Devalaya Chakrabarty will be talking about effect of composition and processing on the microstructure and texture of steels. Then Professor Sumantra Mandal will be talking on the coincident site lattice boundaries. So, what are coincident site lattice boundaries? Then after the lunch break, Professor Nilesh P. Gurao from IIT Kanpur will be presenting online on the quantitative microscopy using electron backscatter diffraction and transmission Kikuchi diffraction. Okay. Finally, and it is slightly different, but it will be good because Dr. M. Arul Kumar from IIIT DM, Design and Management, I think, or Design and Management, Kanchipuram, India, will be talking about development of microstructure sensitive constitutive model. Now, just I will let you know about M. Arul Kumar if you don't know. M. Arul Kumar was working in Los Alamos National Laboratory for the past 15 years, and I think he has taken a year leave or more and joined IIIT DM this Kanchipuram as associate professor, and if he likes it here in India, then he will be here then. So that's all. So I will like to invite Professor Field. The dais is yours. We have to start the lecture. Thank you so much.
Perfect. Thank you. Thank you. Put on my microphone, Neil. Okay. Thank you. All right. Thank you. So we've been talking about texture and been kind of very basic in what we're doing. And now I'm going to talk about something that I don't know anything about. That's triple junctions. So we don't know very much as material scientists. It's probably, if we're talking about polycrystalline materials, it's probably the main thing that's the most fundamental part of microstructure that we really don't know very much about. Right? So we have a lot of different types of characterizations for these, but we really have never been able to solve any problems around these. So I'm going to talk about how maybe we can solve some problems. Okay, so this is all, a lot of it is conjecture, a lot of it is maybe we can do this, maybe we can try and reduce the space and attack it like this. But that's my disclaimer, let's say it's my disclaimer on these slides. Okay, so triple junctions and triple junction textures. Yep, there you go. All I can see on this slide is myself, so making sure it's kind of, anyway. Okay, so this is my typical microstructure slide, right? So I think, let me make myself a pointer thing. All right, so a lot of times when I will give presentations, I'll put this slide at the beginning just to say we're all understanding one another, what I mean by polycrystalline structure. And I'll identify all these different types of features of the microstructure that we might look at. And then I'll say there's also gradients, if we have inhomogeneous materials, there's gradients in any of these or all of these different features of the microstructure. But as you see my little post-it that I put up here, I don't even talk about triple junctions. Right? The one thing that maybe is a triple junction indication is this precipitate that I put, this little where I talk about dispersoids, inclusions, precipitates. I put one right on the triple junction. Now I would do that because triple junctions have the highest diffusivity of any of the other features, right? Compared to grain boundaries or compared to dislocations or something like this. Highest diffusivity, so it's a natural place for something like that to occur. But in general, I'm just using this to say I don't even mention triple junctions when I talk about microstructure, typically. All right, so this is from a paper 20 years ago. And this is showing grain boundary volume, if we consider the grain boundary to have a specific thickness. Grain boundary volume versus triple junction volume versus, this is the top one where it just says interface. That's the sum of grain boundary and triple junction together. That's all that is. And you can see if you look at triple junction, this is for a specific assumption of a grain boundary width of 1 nanometer, right? So we can argue about how wide a grain boundary or a triple junction should be. But until you get down to under 20 nanometers or something, triple junctions are really negligible in their overall volume contribution. So if we're talking about deformation processes, and if we say different deformation process occurs at a triple line instead of at a grain boundary or in the bulk of the material, we can really neglect it if the grains are larger than 20 nanometers or so. There's other features that maybe are important anyway, but if we're talking about deformation processes, they become important, really important under 10 nanometers. So as the crystallite size gets smaller and smaller, triple junctions become more and more important. Okay? All right, so since I said we don't know anything about triple junctions, I present this as a hypothesis. The triple junction character, or triple junction texture, if you want to say that, is important for these different applications. So deformation of nanocrystals, that's the one I talked about, particularly if we're talking about grain boundary sliding. So if you have grains and you get smaller and smaller, even at room temperature for nanocrystals, dislocations can't move through nanocrystals, right? You can't have a dislocation source if you have a nanocrystal. Just think of if you've studied dislocations, there's a Frank-Reed source that requires a certain curvature of the dislocation to be able to multiply. And if you don't have enough crystal, you don't see that dislocation. So different deformation processes occur, and it's usually grain boundary sliding, some type of deformation along a somewhat amorphous grain boundary. And triple junctions control that. Any type of incipient or early on dispersoid precipitate formation, because the diffusive path along triple junction is greater, we would expect those things to happen first along triple junctions. Cavitation is another one of those during creep. So as you get holes that start to open during creep processes, they'll open first at triple junctions. We have seen those kind of things, but this is anecdotal, right? We can't go in and quantify exactly what's going on different types of triple junctions. Control of grain growth, particularly abnormal grain growth. So as grains are growing, triple junctions have to migrate. So the line tension of a grain boundary, that has to allow migration based on triple junction motion. And so if triple junction is more stable and not inclined to move, then those grains will remain stable size, whereas other grains will grow. And so particularly with abnormal grain growth, there's a lot of theories that say triple junctions are controlling this abnormal grain growth. And then finally, I say anything that has grain boundary sliding involved, which goes back to the first slide. And then I put one slide here. I meant to add a whole bunch of other slides for the evidence for existence of why triple junctions are maybe important. But I've only put one slide here, but there's a whole lot that we could put that talk about some of these things I mentioned in the previous slide. This is one where some Claude Batias, Steve Antolovich, Paul Paris, they are fatigue experts, and particularly in ultra high cycle fatigue. So they can fatigue materials at greater than 20,000 hertz, 100,000 hertz. They can cycle materials that fast. And in ultra high strength steel, so this is bearing steel, they're calling it, so it has a strength of about 2 GPa, very high strength. We get these failures that occur what they call a fisheye. So they get this fisheye that they see in the structure, and failures occur from that. And if we go with our EBSD and go look at that, virtually all of these that we have seen occur at a triple junction of a prior austenite boundary, right? So these different color schemes, these are all martensitic type structures. Here's another one up here. So this is a triple junction of a prior austenite boundary, right? You can kind of see that just in the color scheme. But everywhere we saw these type of fisheye structures, they all occurred at triple junctions, where all these failures occurred in fatigue. And fatigue was something I didn't mention on the previous slide, but that's something that these researchers noticed with that. Okay. Now, I'm going to talk about grain boundaries a little bit, and I'm going to use the approach of stereology. Stereology means the study of space, right? Stereo. Do you guys use the word stereo for music these days? You listen to a stereo? We don't even say that anymore, right? So when I was a kid, we talked about, we all had stereos. So they would play and we would have surround sound music, right? So it was filled space, the music filled space. And I always thought stereo meant music, but it actually means space. So stereology is the study of space. And we've adopted it in creating grain boundary character distributions in 5 dimensions. So I'm going to talk about that a little bit. The basic measure, stereological measure, is surface area per unit volume for grain boundaries, right? Because grain boundaries are 2-dimensional features. So how many of those occur of a given type in the given volume, right? And then triple junctions we'll talk about, but they follow very much how we can study them. They follow very much the same approach. So I want to talk about how we do grain boundaries with stereology. So some basics on grain boundaries. We have 2 orientations related to a reference frame, right? So this is the orientations we talked about yesterday in defining texture. So this is just orientation of grain A, orientation of grain B. There's a grain boundary plane between them, and any section of the grain boundary plane has a normal N. Usually our grain boundary planes aren't planar, right? They're curved surfaces, but any section of it has some boundary normal that we can quantify. So we'll use those parameters, which in this case is 8 parameters, right? There's an orientation here, an orientation here. They each take 3 parameters, and then 2 parameters for a unit normal orientation. So that's 8 parameters. So these can be described stereologically. The misorientation shows the orientation between 2 grains. So here's a grain A and a grain C. So delta G AC is the misorientation between these 2, and it can be defined like this. Just time GA times GB transpose, right? The orientation matrices or quaternions or however you want to work, whatever space you want to work in. These H values are the symmetry elements. So we talked about symmetry and how for a cubic crystal there's 24 different physically indistinguishable symmetry elements. So these are the different symmetry elements. And so you go through and you find the minimum, usually the minimum angle misorientation is usually what you define based on this equation. And then you need the grain boundary plane. Triple junctions include 3 misorientations instead of just 1, right? So if this is the triple junction, we have all 3 of these misorientations, or 3 orientations if we prefer. And then we have the boundary normals for each of these, and we have a direction of the triple line orientation, right? The way the triple line is pointing. So a lot more parameters with triple lines than we have with grain boundaries. So this is looking close at a triple junction, and this is just being, you know, very idealistic on what a triple junction would look like. If you cut through a section plane and you see a triple junction, you don't know which way that triple line is pointing, right? In this case, it's pointing out, coming out at an angle, and then all those boundary planes, you're not showing which orientation those are by looking at the plane. You can look at 3 dimensions, right? We do that sometimes. We look at 3 dimensions, but then we're very limited on how much space we can look at, right? And we'll talk about why that's a problem. Okay, so different features. We have the triple line orientation, which here I'm calling T, which I'll apologize in advance. I also use T for a scan line test direction, a test scan line direction. I use T as well, so I use T for 2 different things, so sorry about that. But T is the triple line direction. We have 3 orientations, A, B, C, and the misorientations. We have 3 boundary normals. And then we have these angles between the planes. We call those dihedral angles. And the dihedral angles, as you see on a plane surface, aren't necessarily the true dihedral angles, right? So you can't measure those directly from a section plane. You need the 3-dimensional data, or you have to go in stereology and pull those out. And then this is just the external reference frame. Okay, so if you count up all of these parameters, let me see what I have here. So if we count up all of these parameters, we'll say, okay, 3 orientations for each of the 3 parameters for each orientation. That's 9 parameters. 2 orientations for each boundary plane. That's another 6 parameters. And then we have 2 orientations for the triple line direction. That's 2 more parameters. So that's 17 parameters that triple line space is, right? So we'll say it lies in a 17-dimension space. It's a big space, right? 3 dimensions is too much for me to think about too much. If I go to 4 dimensions, I'm like, okay, 17-dimensional space. Now we can reduce that because, of course, if we have 2 boundary normals, we know what the line direction is. So we can throw the line direction out. We don't need to know that. If we know 2 boundary normals and a dihedral angle, then we're going to know the other orientation. If we know 2 misorientations, then we know the 3rd orientation, just for crystallographic continuity, right? If we have a misorientation between A and B and between B and C, then we know the misorientation between C and A has to take us back to the identity, right? So we can throw that out. So it takes us down to 11 dimensions, okay? So we've gone from 17 to 11. That really helps us, okay? Now, if we look at grain boundary parameterizations, we can define grain boundaries with all kinds of different things. We can look at a misorientation distribution, ignore the grain boundary plane, that's 3 parameters. We can look at some orientation in the distribution of the texture, some orientation, and say what boundary planes are most likely to occur with this orientation. Maybe the boundary planes all lie on 110 planes, right? So then if we know the texture, we can say, well, here's where most of the boundary planes are going to be. We can do it with 5 parameters. This is kind of the standard one we use, where we use a misorientation and a boundary plane. And we can do that either in the reference space or the crystal space. We know how to measure both of those. Or we can do 8 parameters where we include the external frame. So why would we use 8 parameters for a grain boundary? It's because if we're looking at any kind of deformation situation or any kind of external magnetic field or heat gradient, something like that, we need an external reference frame. If we're looking at where the slip planes are and how they intersect with the grain boundary, 5 parameters doesn't help us because we don't know how our orientations are aligned with our stress axes, right? So then we would need that additional external reference frame. So the grain boundary, if we're talking about deformation, you almost always have to use 8 parameters to define the grain boundary, which makes it a much bigger space. So we usually ignore that, think about energetics of the boundary, how they form, use our 5 parameters, okay? Triple junctions, we can do the same thing, right? We can define all these different things where we're saying Here's an orientation with a triple line orientation, right? So if we have a preferred orientation in our texture, what's going to be our triple line orientation? Maybe it's going to be from processing, right? Maybe we have rolled structure where all our triple lines tend to line up in the rolled direction, right? Maybe that's something that would occur. And then they would correspond to what our texture is as well. And so some of these types of features. But if we're doing everything, we have to add that external frame, which gives us 14 parameters. Or we'll stick in this smaller 11 parameter space. All right. So there is a term in statistics called the curse of dimensionality. Right? So if you talk to statisticians, they'll use this phrase, curse of dimensionality. And this is what it means. So our good friend Bunga, who you've heard his name several times, he's, in my view, he's the godfather of texture, right? Everybody recognizes Bunga as the man, right? He's the godfather. He was one of the earliest people, not the earliest one, but one of the earliest people working, and then he was the most consistent all the way up through his passing. Okay? And he's the one that wrote the Bible, right? He wrote the red book, the Texture Analysis of Material Science, 1969, he wrote it. Translated, it was in German, translated to English in 83. All of us use that book. Okay? It's one of our main references. So anyway, so this is from the Godfather. And this isn't a perfect analysis, but if you're thinking of statistical reliability, this is the guidelines he gives. It says, so if you have a given dimensionality of your function, so like a texture analysis, you have three dimensions. You have your 3 Euler angles, for example, right, or 3 Rodriguez vectors, or 2 angles and two polar and azimuthal angle and a rotation angle, right? Any of those 3 parameters. Then for reasonable low statistical resolution, you would need 10 to the third. So this is log times the number of data. So for 3 dimensions, you would need 10 to the third measurements to have any statistical reliability. Now that's not always true, right? If you have a single crystal or a very heavily textured material, you would need fewer measurements. But for a random unknown texture, you should have 1,000 measurements at least to even say you have any kind of statistical reliability. For good statistical reliability, you need 10 to the 6th. So this is 10 to the n, where n is dimensionality. This is 10 to the 2n. Okay. Grain boundaries, if we're in 5-dimension space, we need to look at 100,000 grain boundaries to be able to say we have any kind of statistical reliability. Can we look at 100,000 grain boundaries? Yeah. When I was a grad student, we couldn't, right? I was doing measurements by hand of orientations, and so I did maybe 20,000 grain boundaries through my grad student career, something like that. I looked at grain boundaries. But you can do 20,000 in a few minutes now, right? If you have a great big EBSD scan, flip them all out, you get 20,000. Can you do 100,000? Sure. Can you do 10 to the 10th? 10 billion? Probably not, right? You can do somewhere in here. 1 million you can do easy enough. A few million, maybe 10 million, right? 10 billion, I don't think we can still do that, right? I don't think we can do that one. Now, what did I say the dimensionality of a triple junction was? Okay. 10 to the 11th. All right, that's 100 billion. Triple junctions, that's not orientation measurements, that's triple junctions. So you need a bunch of orientations so you know where the triple junction is. Can we do that many? Probably not. 10 to the 22nd, I don't even know how to say that what that one is. Bajillion, gazillion, something like that, right? So statistical reliability becomes a real problem. So this curse of dimensionality is why we can't go in and interrogate the space of triple junctions and say this is where all these things are happening, right? What's our preferred triple junction in our triple junction texture, right? What's the preferred triple junction? I don't know, it's 10 to the 11th space, we can't measure it, right? So that's the problem. So we have to figure out how to reduce that dimensionality and how to figure out how to get more measurements in less time. Okay, so that's posing the problem of why triple junctions are so difficult to just go in and experimentally analyze. Now we can go in and look at very closely at a single triple junction, right? We can do measurements in TEM. We can see where that triple junction is. We have it perfectly identified. We can model with atomistic simulations or DFT or something what's going on at that specific location, and we can learn a lot about triple junction. There's a lot of work in that area. Okay? And then we have, whoops, wrong way. And then we have a lot of people who will go in and identify triple junctions based on what the grain boundaries are. Later in the day, we're going to hear about CSL boundaries, and I'll mention them here a couple of times. So what's this? If this is a special grain boundary, then let's assume the triple junction next to it is also special, right? So we can kind of do that kind of analysis. Or if we have a network of triple junctions and we see how the grain boundaries evolve generally, then we can infer something about the triple junction distribution or the triple junction connectivity we can infer something about. So there's papers in those type of areas. There's something called U lines and I lines in triple junctions. And it's talking about the character of the boundaries that form those U lines or I lines. So you can categorize triple junctions saying this is a good triple junction or a bad triple junction. It has special features or it has not special features, right? U and I lines we call them. Okay? So there's a lot of work in these types of areas in triple junctions. But it's assuming a lot, and it's not understanding what the true space of the triple junction is. Okay. So we do three-dimensional measurements. This is just a 3D stack that's made up from EBSD data. It's just done with Dream 3D. Dream 3D is a software, still free software, but maybe changing soon, right? Still a free software you can just go download and use it. It's come out of a number of people, the Air Force Research Lab, and Tony Rawlitz contributed a lot to it from Carnegie Mellon, Liz Holm, who's at Sandia before. So there's quite a few people who have contributed to this software. And it's available, right? Blue Quartz is a company, and they just give the software away. It's just kind of cool for a company, okay? In general, if we're looking at this, you know, a distribution like this made with a dual beam fib is going to take 3 days. And the size of this is maybe 50 microns on the side. 50, maybe 100 microns. You could do 100 by 100 by 100 microns cube with your standard gallium ion fib dual beam system. You get cool data, but you're not going to get 1 million triple junctions, right? You might get 1,000, right? If you spend a lot of weekends and do that, then maybe you'll get several thousand, okay? You can do a little bit of stuff with diffraction contrast tomography on synchrotron or in the lab DCT. You can measure high energy diffraction strategies where you can look subsurface and get boundary plane information. So some of these things you can do. Stereology is where you can get the most triple junctions or grain boundaries into your distribution. So this is identifying a little bit about grain boundaries, what special boundaries are. And I'm not going to focus on this very much. Check my watch here. I'm not going to focus on these very much, particularly because you're going to hear about coincident site lattice boundaries a lot in the future. But a lot of times we'll just say, you know, if it's low angle boundary or if it's one of these special boundaries, then it's low energy, so it tends to be stable. It's low diffusivity. Sometimes high mobility, sometimes not, right? Mobility is a little kind of tricky. And then these triple junctions defined, like I said, from specialness of grain boundaries. All right. So all of these presuppose some kind of specialness criteria, and you can't go in and make a full set of measurements. So what we have to do is reduce our space. But first I'm going to talk about stereology and how it works with grain boundaries, just so you get a feel of what stereology is. Okay. So here's 3 dimensions. Here's some ways to do it. Stereological techniques. There's a number of different techniques to measure this surface area per unit volume with a given grain boundary normal orientation n. Okay? So I'm going to talk about a couple of these. Hilliard published some work in the 1960s, so now 60 years old, these papers. Really, really fantastic solutions he got. That's very complicated mathematics that comes up with just such a simple solution. So simple. Brings a tear to my eye sometimes. It's just such a simple solution. It's just, you go through all this complex stuff and you say, really, that's the answer? It's just 1 + 2? Wow, perfect. Okay. Anyway, so we have this feature that we can measure. This is points per unit length along a scan direction T, right? Not a triple line orientation. This is a scan direction. So if I scan in some direction T, and I intersect a grain boundary plane, and that grain boundary plane has a normal n, then this is called the fundamental equation of stereology for this problem. So this is the function I want to know, the surface area per unit volume with boundary normal n. And if I scan in enough directions t, and I integrate over this space of all n's, I have t dot n, right? So if they're aligned, then I have a lot of those, and if they're not aligned, then I won't have any intercepts, right? So I have a normal, and I have my boundary plane. If I scan in this direction, I'll intercept it a lot. If I scan in this direction, I won't intercept it, unless I scan in a different direction. Okay? So that's what it is. It's basically geometrical statistics. But this equation is it's mathematically derived equation. There's no assumptions involved in it, except that you're scanning in all directions. Right? You have data in all directions. You have boundaries in all directions. This is a second type of stereology, where you say you're measuring, this is the grain boundary as you see on the plane, and this P is the normal to your scan plane, to your test plane. So you cut your specimen, you polish it, you look at it, you see a boundary. So the orientation of that boundary, the angle, measured with respect to some reference, you take that, which is an omega, right? So scan, this is your test plane normal, and the angle of your boundary trace. You want to know this entire function, surface area per unit volume, and it's related through this equation. Now both of these you can represent either in the external reference frame, or if you think about it like Greg Rohr and Dave Saylor did, they came up with this beautiful solution where instead of using the external reference frame for each of these, they use the individual coordinate frame defined by the orientation of the crystal. Okay? And so this becomes one coordinate frame with that boundary. This one becomes another coordinate frame with that boundary. Right? You can do that through all these spaces. So now if I'm measuring 1,000 grains on my EBSD scan, all of a sudden I have 1,000 different coordinate frames of all different orientations, or different orientations based on the texture of that material. Okay? So now I have covered this orientation space, this space of different scanning sections, and I look at T, my scan direction, based on the crystallographic coordinate frame. What crystal coordinate frame am I scanning in? Okay? So it takes a little bit of mental gymnastics to go from, okay, I'm scanning in this coordinate frame versus, okay, for this grain I'm scanning like this, and for this grain I'm scanning like this, right? So all different coordinate frames. But once you do that, once you have that, then you don't have to go cut your specimen a million ways, right? Then you can just cut it and get all the coordinate frames, which is kind of cool. All right, so each of these parameters, each of these things we want to measure, this is the one we're measuring, points per unit length, for example, and we can represent that in a Fourier series expansion. This is called a spherical surface harmonic function, which when you get into the mathematics of texture, this is Satyam Suwas showed some of this yesterday. Just very quickly he showed it and said it's in the notes, don't worry, it's in the notes, right? But this is a spherical surface harmonic, so it's defining over the two-dimensional orientation space. And you can come up with these coefficients that you can calculate very simply based on, not this equation, this is the solution. But you can calculate these based on your knowledge of what the spherical harmonic is. So each individual measurement you take, you calculate these directly. So you know this function. This is the function I'm scanning in this direction t. I have this many intercepts per unit volume, right? So I can do that. I can do that directly. And then this known function I can represent in a Fourier series expansion over the same space. Right now it's not a scan direction that I'm representing, it's the boundary normal orientation. But then I go back to that fundamental equation of stereology that I showed you before, that integral equation where you have a t dot n and you're integrating over the space of n. And once I do that, I put in all these Fourier expansions. This is the solution I get, right? Where my S coefficients are known in terms of my S prime coefficients. So I'm measuring directly, and I've actually done this backwards. I'm measuring directly the S coefficients, which would be these. So I'm actually measuring my S prime here. So this slide should have S here, and it should have S prime over here. But I measure this directly. I get the coefficients out. This is just algebra. These are just algebraic values. Now the mathematics to get to this solution is very, very, very involved. You go to Hilliard's paper and read that about 100 times, and then you'll understand it. That's how long it took me, about 100 reads, right? Then all of a sudden I just said, wow, it's a very, very simple solution. So I take what I measure, I grab those coefficients, I do some simple algebra, and then I know the coefficients for surface area per unit volume, where I've never actually measured the volume, the grain boundary normal. I haven't ever measured a grain boundary normal. I've just measured how many times I hit that boundary with a given scan line. Okay? And then I can add crystallographic dependence. Right, so the equation I showed you before was just this equation without this delta G. Now I can add the delta G in, or I can add GA and GB independently. And I say, okay, I have this many intercepts of a grain boundary that has this specific misorientation. So now this is a 5-parameter space. My stereology is still in just the standard 3 dimensions where I'm pulling out n, the boundary normal. But I just add in the stereology for the function. So it increases the dimensionality of this space, so it becomes a much more, requires many more measurements because I have that additional 3 dimensions. But the stereology is the same. And then I can do some beautiful things, and I can do it with this other type of stereology as well. This one requires a solution of a set of linear equations. So it's not quite as straightforward and simple, but it's still just a set of linear equations that we know how to solve. Okay. So now we have it in 5 parameters. If we're looking for triple junctions, we know that equation, right? We need to know the line length per unit volume. That's the space a triple line lies in, right? So it's a line length, it's not a surface area, line length in some direction t. The direction here is defined by phi and theta. And then I have this surface, my plane section surface normal defined by omega and psi. So I just have that equation I can go through. It's the same type of stereology. And the same type of solution exists that I can get. And of course we can add all our other parameters in there, so we can do this in 11 dimensions if we want. Get out our values. All right, so we wanted to measure this in our lab, but my graduate student didn't want to do 10 to the 11th measurements. So he said, let's try and figure out a way to get less parameters. He said, let's just look at it if the triple line contains a coherent twin boundary. Now, coherent twin is a misorientation of 60 degrees about 111 in FCC, 60 degrees about 111, and the boundary plane normal is along the 111 plane. So that's 5 parameters of the distribution that you already know. Okay? So out of that 11, I have 5 that are known. I'm down to a 6-dimensional space. Now he only needs 11 measurements. He said, okay, I can do 1 million measurements. No problem. Okay? Maybe he did 2 or 3 million, but we can do that. Okay, so this is reducing the space, and there's a lot of assumptions you can put in saying, okay, well, if I have a triple line, then the dihedral angle is not going to be 360 degrees, right? It's going to be some fraction. So he didn't allow the dihedral angle to be more than 180 degrees. That was something he said, I'm just going to ignore that part of the space. And that allowed him to calculate things easier just by cutting down the space. So he made these types of assumptions. But again, he just required a triple line with a coherent twin. Now, what kind of triple line is that? If you think in your mind, well, I have a coherent twin that hits a grain boundary, that's not really a triple line, right? It doesn't really tell us a whole lot about what we want to know in the microstructure. But it's a way you can do the calculation, and it's tractable experimentally. I'll show you an example of why it might be useful later, but right now, he just said, I just wanted to track this. So then he looked at this and said, okay, let's look at this stereology. And he created a numerical microstructure. So he created this fake microstructure where he had a really strong peak in the triple line distribution, triple line orientation distribution. And he said, let's use 500,000 measurements and represent this in this type of space. And that's 500,000 measurements. If he used only 5,000 measurements, it looked like this. Right? So the triple line was in this position, and he could see it pretty good. Almost you could see it here at about 25,000 measurements, but you get to 10,000 or 5,000, he couldn't see it anymore. And this is for a very simple distribution where you have a really strong peak. It wasn't a delta function, but it was close to a delta function, approximating that that's the only triple line in the distribution. Okay, so 500,000 measurements, he could get a pretty good distribution. And then he said, well, let's show one that is a true distribution. So let's not make any stereological measurements. Let's just look at what it should look like. And this is positive and negative hemispheres of a stereological projection of where the triple line orientation is going to lie. Right? That's what this is showing. This slide just has a lot of circles. Okay, but this is the known function. So this is the function he put in. And then this says, let's measure this with stereology, and let's use 500,000 measurements. And so he pulls it out, and it comes out pretty good. Right? Comes out to where you can see pretty much looks like the same distribution. And you can do some quantitative metrics to compare these, and he's done some of that work in some of these papers. But you can pull that out. All right, so this is from the different types of measurements. I think I showed this. Did I go the wrong direction? I just showed it again. That was my mistake. Okay. So then another student said, let's look at a few different types of distributions. And he said, these are the ones where I'm going to have a lot of triple lines. So he just came up with some made up distributions. And he said, let's look at only the triple line stereology. So he was ignoring crystallography, just looking at 2 parameters. So you can do that much easier. So this is his true distribution. This is with 10,000 measurements. This is with 1,000. This he did all at a truncation order of 8 in the Fourier series expansion. Now let's go back to the Fourier series analysis that Setiam showed yesterday. As you use Fourier series to represent your functions, it requires that you go to infinity in Fourier series expansion. Typically in texture, we'll stop at about 20, right? 22, 34, sometimes 46 we'll go to. We have specific values people use. We never go to infinity, right? Computers don't like that. This one he stopped at 8. Okay, so this series expansion is represented at an order of 8 with different numbers of measurements. So is this correct? Ish, you know, it kind of looks correct, right? That he gets it. This one is not correct. He found a flaw when it comes to very precise types of distributions. So he said, let's say we have 2 line orientations that are 90 degrees from each other. So it should look like this in 2 dimensions. When he took a lot of measurements, it looked like this. And if you think about how maybe that would happen stereologically with the measurements, it makes sense that it would be like this. Stereology assumes random sectioning on structures that have no specific symmetry in their distribution. Okay? So that's one of the caveats of stereology, something we learned kind of recently in our game here. But we still like to use stereology, so we're still using it. We just remember that it's not always perfect, right? All these tools we use aren't always perfect. All right, and I wanted to show this. This was published yesterday, according to, I mean, I saw it a few months ago, obviously, but January 15th it was published. Greg Rohr's group. He's really kind of the other group. He's at Carnegie Mellon. He's kind of the other group that does a lot of stereology and playing with triple junctions. So he published this. This is in nickel. He used a nickel system, and he said, we're going to look at a triple line with 2 coherent twin boundaries. Right? So he reduced the space way further than what we reduced it. So he has 2 coherent twin boundaries, and he's looking at that triple line orientation. And he's trying specifically to see where the orientation of the next boundary is. Now, if you have 2 twins that connect each other, they're going to make either no grain boundary, right, a sigma 1, or a sigma 9. Sigma 9 is the second order twin, and there's 2 specific boundaries in the second order twin, a 112 or 114, depending on how that is arranged. 114 tends to have a lot of mobility, 112 doesn't. He found a lot of 112s in the distribution, didn't see any 114s in the distribution. Right? So you can use that to say, okay, these boundaries are all moving away, so they don't exist. This is the ones we see in the distribution. So he's using this approach with triple lines to trying to understand a little bit more about the twinning process in nickel, which is kind of interesting. Okay. No reported measurements of complete triple junction distribution functions. Nobody's ever claimed they've measured one in 11 dimensions. Maybe we can figure something out if we reduce the space either by 3 parameters or by 5 parameters like we've talked about. And maybe from that, maybe from these reduced descriptions, we can learn something about whether triple junction texture is actually a feature that is controlling in deformation of nanocrystalline materials or in precipitate growth. So far, 11 dimensions is not going to be possible. 10 to the 11th measurements we're not going to be able to do. Maybe in the future we can, right? We're getting way faster than I ever thought we would get. When we first automated this back in the 90s, we got 1 measurement every 2 seconds. That was fantastic, right? I would start the measurement, I'd go play basketball for a few hours and come back and have 10,000 measurements. Fantastic, right? People say, you're just playing basketball. No, I'm working. It's taking measurements. Don't worry. Working. Right? The good old days. Good old days. Okay. Maybe it will get fast enough we can measure these, but hopefully we have all these tools in place so we can actually learn in the meantime. All right. That's the end of my main presentation. I'm happy to take any questions. Okay, so the question was, is it good enough for two-dimensional EBSD, or do we have to measure 3 dimensions? I think with current strategies, 3 dimensions, we're way limited on the number of triple lines we're going to be able to see. Right? So 3 dimensions, we'll be able to measure thousands maybe of triple lines. If we're looking at 2 dimensions and using stereology, we'll be able to look at millions of different triple lines. That's with today's technology. In the future, maybe we'll be able to look at 10 to the 11th. In either case, I don't know what's going to happen with 3-dimensional imaging. But right now, the main, my recommendation would be to use stereology like we do with grain boundaries now. Right, so grain boundaries, we almost always use stereology. We're kind of getting to the point where we can do hundreds of thousands of grain boundaries with 3 dimensions. So more and more you're seeing people use 3 dimensions instead of relying on stereology. But if you look at your software, your MTEX or Oxford or EDAX software, any of that, all of those are stereologically based to do 5 parameters if you're getting the grain boundary plane.
Just below, push it once.
Okay. What I'm saying is, if we reconstruct the grain in 3 dimensions, the actual shape, measure from the EBSD, to be able to reconstruct the grain shape, then we need not to calculate any parameter.
Right, so the question is, if we do it in 3 dimensions, we reconstruct the grain shape, then we don't have to use these stereology techniques to reconstruct what the boundary normal distribution is.
Yes.
That's exactly right. Then you have the direct measurement of it. That's exactly right. Yes.
So, yeah.
I agree.
So, is there any more question? Okay.
Sir, are triple junctions mostly important in nanocrystalline materials, or in bulk scale materials also? They are an important microstructural parameter.
Yeah, so I tried to show a list of what I thought was important about triple junctions. So if you're worried about cavitation in creep, or you're worried about precipitate growth on grain boundaries or on triple lines, then it might be important for standard materials. If you're talking about controlling deformation processes, I think it's only going to be important in nanocrystalline. And that probably means below 20 nanometers grain size, so very small grains.
So from a deformation perspective, mainly nanocrystalline materials.
So from a
deformation perspective, mainly nanocrystalline materials will be.
Right, for deformation, just nanocrystalline is going to be important, I think.
Sir, the triple lines that we are talking about, they may not be the mathematical line, means they may be curves. So will that increase the complexity? Similarly, for grain boundaries are not a plane, mathematical plane, there can be curvy planes. So will that increase the complexity?
There it is. Okay, so the question is the fact that triple lines aren't straight lines, does that cause trouble? So just like with planes, right, grain boundary planes, they're not planes, but if you take any segment of that, you can have a grain boundary normal of that segment, and then you move to another segment. So what the stereology shows is the fraction of triple line that is pointing in that direction, and it doesn't matter how curved it is. It's showing the fraction pointing in this direction. So it could be a plate of spaghetti curved line, and you can still measure what the preferred orientation of that spaghetti is. Okay? Or a plate of noodles, yeah?
But if a precipitate has to precipitate, it will not see a triple point, but a triple line it will see inside 3D. So means it still remains a curvy line.
Yeah, it's absolutely curvy. So you don't know how it's curved with the stereology I've mentioned. You can do stereology of curvature. So we could pull curvature out as well. Would require more work, more measurements. But we can do curvature as well from plane sections, for example. We know how to do that. But the fraction of line pointing in a given direction is what stereology gives you. It doesn't tell you how those are connected. There's no information about how things are connected in stereology. So if it says you have a boundary plane or you have a triple line, you don't know what the next triple line next to it is. Right? There's no spatial information of how it's correlated. You just know how many are pointing in this specific direction with this specific crystallography.
So I'm not going for any more questions because time is up now, and Dave is here for the entire time, so you can just discuss with him. So thank you, Professor Field, for giving this wonderful lecture on triple junction. It's really different, and we should really know this. And there is a small gift for you. And Professor Devalaya Chakrabarti is here. So I would request Professor Devalaya Chakrabarti to give this small gift. Like thank you, Dave. Now, our next speaker today is Professor Devalaya Chakrabarti. Devalaya Chakrabarti, as you all know, he is faculty in our department. He has been a pioneering researcher in steels, and he had a lot of manuscript or papers which are very essential if you are working on steel and deformation and properties of steels. So he is going to present a lecture on steel itself. So welcome, Professor Devalaya Chakrabarti.
Because I have a class from 11, I have asked the students to stay for some time. So let us continue, and here I will talk about the microstructure and texture of steel, which is a very vast topic by itself. So here I would focus more on transformation, microstructures, different types of microstructures, how they are produced in steels, and obviously some part of crystallographic texture would come into that. And mostly, as I said, I will focus on transformational microstructure and texture, not annealing texture, because that is another very big field, cold rolling and annealing, that develops different types of texture which can be very important for formability point of view. So I must first of all acknowledge that basically whatever I am going to talk, they are not my supervisors, but we all are immensely benefited from their research. Professor Badishya, whose books are very well known, and if you see this particular benite in steels, I have chosen this cover because in the latest edition the cover has changed to benite plates in 2D, but here you can see this surface relief. So, it is a clear definition of displacive transformation, which is deforming the surrounding austenite and producing a surface step. So, it is an evidence of displacive transformation. And Professor Arkera and Professor Jonas, their paper is a pioneering paper, review paper in International Materials Reviews 1990, transformation texture in steel. So, if you would like to learn about the texture in steel, this is the first step, that you must read this review paper, and there is another paper on cold rolling and annealing of steel, which I am not getting into. So, with this let us delve into the topic. So, this is the iron carbon phase diagram, you all know. These are the background slides. There is a high temperature, there is a delta ferrite transformation, which is of immense importance. Then in steel part there is up to around 2% carbon. Then we have austenite, which is FCC, which eventually transformed into ferrite, BCC ferrite. Whether BCC ferrite form first or orthorhombic cementite form first, that depends on the carbon content or carbon equivalent. If it is a low carbon steel, then pro-eutectoid ferrite that forms, and there is an eutectoid reaction. In ferrite, the solubility of carbon is very low, that is the one takeaway message. At 723 degrees centigrade, only 0.025 weight%, at room temperature 0.006 to 0.007. Whereas in austenite, which is FCC, which is more closed pack, 2% carbon dissolves. So, there comes the first questions people ask, why so much carbon goes into austenite compared to ferrite, number one. And number two, whether carbon in austenite and ferrite, if they go into solution, would they have the same effect on strengthening? This is the second questions often asked in the students' viva voce. With this, I move into the next slide. I will answer this question very briefly. So, as I said, there is a peritectic transformation that happens particularly in low carbon steels, which we generally use nowadays, because low carbon benefits our formability, toughness, and most importantly weldability. So, we prefer low carbon steels in modern application, unless a very high strength or very specific requirement is there. Then there is a reaction that happens in the eutectic, which happens in the cast iron part, and a very important reaction which is eutectoid, where austenite transforms into ferrite and cementite. In peritectic, delta ferrite and liquid together forms austenite. So, if you are cooling slow, what happens is, if you form delta ferrite nuclei, it grows, and then you will find inside the liquid at the boundary of delta ferrite, austenite starts forming. So, as the austenite starts growing, the diffusion has to happen through the austenite layer, like the oxide reactions, and as it grows, the reaction would become slow. So, peritectic reaction is generally very slow, and if you want to avoid it, one way is to cool the steel fast, because these domains, high temperature domains, if you have studied phase diagram, those can be extended. So, you can extend the austenite domain, so you can avoid delta ferrite directly get into austenite, that people tries. Otherwise, you have to do some heat treatment and things to get rid of it, because it can be prone to cracking. That is a problem that happens. Otherwise, as I have already said, that you either go for pro-eutectoid ferrite and then pearlite. Pearlite is a eutectoid product of ferrite and cementite. Typically, it is of lamellar structure, but the structure may change. Otherwise, another problem in hyper eutectoid steel is the grain boundary cementite network, which affects the properties, makes the structure brittle. So, we think how to avoid it, apart from pearlite in the middle. A very basic phase diagram funda that you may know, that if two phases has to be in equilibrium, then chemical potential of a particular species has to be the same in both the phases. So, here A and B are, it is a binary system with A and B atoms. Now, the chemical potential of A, that is molar free energy of A, has to be the same in both alpha and beta phase. Then only there will be no diffusion, and there the two phases are in equilibrium. The same is for B, and to get into that point we have to draw a common tie line. So, often we draw a common tie line. to see whether the chemical potentials are the same and what would be the compositions when they are in equilibrium. Now, one important aspect that is there in steel, say here ferrite, BCC ferrite dissolves less carbon. So, we are drawing it at the lower carbon side, its free energy composition diagram. Austenite FCC can dissolve more carbon, so it is at the right hand side. Now, if you are working with any average composition in the middle, what are the choices that are there with you? So, if you are somewhere here, suppose in austenite, this is your average composition and I am coming down through this line. So, what is the choice left with you? That is the question. What would be the transformation? Here the answer is you have one choice left here, that you transform it into a mixture of ferrite, and in this side there may be cementite, which can be represented by a line which in equilibrium will follow this. If you extend this straight line, it will meet its free energy. So, it can dissociate into ferrite and cementite, and by which you can reduce the free energy of the entire system. Now, there is a point here, and the equilibrium locus, the compositions at the equilibrium points, if you plot it for different temperatures, this is for a particular temperature T1. So, you see the composition of austenite curve in blue, composition of ferrite curve in equilibrium with austenite, carbon content in ferrite in equilibrium with austenite in the black. And there is another contour that you will get in the middle in the red, where the free energy of austenite and ferrite are the same, equal free energy. So, if you see, if you are at the higher carbon side of austenite of that composition, then is it possible to transform that austenite directly into ferrite, a single phase ferrite? That is the question. So, if you see you are at this point in the free energy curve, and if you now want to transform it to a single phase ferrite, what will happen? You see what is happening? The free energy is increasing. So, only option, as I said, is left with you is dissociate into two phases, because you cannot transform it into single phase ferrite, because your free energy would ultimately increase. But if you are in the left side, that is, if your composition is below the T0 composition or T0 line, carbon content is below the T0 line, you end up with two options. You see, you are somewhere here in austenite, you cool down, you can produce a ferrite of same carbon content. Now, whether the carbon will remain or carbon will leave, that depends whether it is a martensite or bainite, but you can achieve a kind of displacive transformation without any requirement of carbon partitioning. Yes, another option, if you can want to reduce the free energy further, you decompose it into two phases, come to this tie line and you decompose. So, the point is, if my composition is below this T0, then only I can transform it into a single phase ferrite, BCC or BCT, okay, depending on the carbon content. So, that is the significance of the, so bainite transformation, martensite transformation, this happens when the composition is below this. Martensite, yes, you can quench and store any kind of structure, but it is very much true for bainite transformation. And at what temperature transformation would happen? That is another question, because you see this much driving force is there. This is the change in free energy. Whether that is sufficient for you to nucleate a new phase, that is another question. It may not be. If you are just below this T0 composition, it may not be sufficient to cause the transformation. There are two reasons. You have to nucleate. To nucleate, some kind of dislocation reaction is required, as per Olson and Cohen paper in 1975-76 their work. So, some kind of dislocation dissociation is required. So, that nucleation requires some amount of energy, plus this kind of transformation is associated with huge strain. You will see how much shear strain is involved. So, lot of strain, lot of an interface will produce, dislocations and twins may need to be produced to get this kind of features. So, this entire energy can be quite high, 700 joule per mole, something like that. So, if your net decrease in free energy exceeds all these increase in energies, then only you get the nuclei. So, the BS temperature or MS temperature is decided by that, whether your decrease in free energy is exceeding the magnitude of increase in energy for nucleation as well as strain, that is a major component associated with the transformation. Because in other way, if you consider strain, this ferrite free energy curve will actually go up, right. So, this curve would go up. So, it will add to its free energy. So, now let me very quickly show you some slides. Carbon goes into octahedral interstitials in BCC as well as FCC. Here we are showing the octahedral interstitial site in BCC, and the same, and there can be calculations of the strain it produces. Here we are showing the carbon getting into the octahedral site in FCC, which is edge center position or the body center position. Now, the summary of this are given in this slide, that size of iron atom you can see here, size of octahedral void in FCC you can see here, tetrahedral void is even smaller, size of octahedral void in FCC you can see here. So, now if a carbon atom size is also shown here. So, if a carbon atom of 0.77 angstrom would have to go into a void, which void would it prefer, right? Between octahedral and between tetrahedral, it would prefer octahedral voids, because in both case FCC and BCC you see octahedral, sorry, this side right hand side is BCC, it is a typing mistake. This F will be B. So, here it is written B. So, these will also BCC. Okay. So, it will get into octahedral void, number 1, and number 2, it will prefer to get into octahedral void of FCC, because there the octahedral void size is larger. In BCC, if you see, the octahedral void is much smaller. That is why carbon preferred to dissolve more into austenite, and carbon content can be 2%. Whether much lesser carbon, only 0.006 carbon goes at room temperature into BCC ferrite, because of the smaller octahedral void in BCC compared to FCC, whereas larger octahedral void. So, the numbers and things are mentioned here. Another important thing that is written in the below lines, the distortion caused by carbon atom in octahedral void in BCC is asymmetrical, whereas in FCC it is symmetrical. If you see, if you put a carbon atom at the face center position in BCC, and if you see the distance of the neighboring iron atoms, you will find in all side it is A by 2. This side also it's basically equal. You will find in FCC you will find the atoms are at equal distance. So, sorry, in FCC you have to put in edge center. If you put an edge center, you will find the face center atoms are at A by 2. But in BCC you will find, if you put the atom at face center position, you will find the 2 atoms which are at the base center, they are at A by 2, whereas those at corner are A by root 2. So, naturally they push the atoms in BCC differently. The corner atoms would be pushed more, the body center atom would be pushed less because they are away. So, it creates normal strain, but the magnitude of the normal strain are not same. And we know the magnitude, if they are not same, then there will be a deviatory component, there would be a shear component. So, there will be some kind of shear tensor accompanying with it, and screw dislocation tensor is pure shear. So, screw dislocation will be hindered by the carbon atom in BCC, because its strain field is containing shear components, whereas in FCC it is a dilation component only, and you know dilation component is there only in edge dislocation, dilation and shear both in edge dislocation, right. So, carbon retards the dislocation more in BCC iron, because it interacts with the shear component of both edge dislocation as well as screw dislocation. So, you will get higher strengthening, but in FCC you get relatively lower strengthening, because it interacts with only the edge dislocation dilation part of the tensor. So, quickly 2 points we have covered. One more important aspect in steel is the carbon equivalent, that not just carbon that decide which phase to form, there are elements which play similar role as carbon. So, there are two very well known societies and institutes who have proposed two equations, and you have to consider all these elements. Even if you are working with a low carbon steel, your carbon equivalent is high, then it can behave as if the total carbon content is higher, and accordingly the formation of the phases would be decided. Now, if you cool a steel at different rate, we know different phases form. Very slow cooling, we get quartz ferrite with cementite, together they may form eutectoid phase pearlite. Relatively faster cooling or isothermal holding, we get bainite. Even faster quenching, we tend to get martensite, and we prefer to temper martensite to soften it, so that it gains some ductility, otherwise martensite has a poor ductility. So, the question is where from all these phases are coming. So far we have talked about diffusional transformation and displacive transformation without any atomic partitioning, and we now try to understand more about the displacive transformations. You may know about the TTT and CCT curves, because in phase diagram non-equilibrium phases like constituents like bainite and martensite are not there. So, those are there in the TTT. So, if you go into TTT diagram, you see there is a bainite bay and there is a martensite bay. So, this is the flat line that tells you MS temperature, and if you go below there is a MS temperature, MF, and all those lines will come. And if you cool slowly, you get ferrite, if you cool little faster, you get finer ferrite, pearlite, and so on. Now, when we add alloying elements, sometimes suppose we add molybdenum. So, it is a more accurate TTT diagram for an alloy steel containing elements like molybdenum, boron. First of all, what these elements do? These elements slow down the diffusion in austenite, increase hardenability, and some of these elements segregate to the austenite grain boundaries. So, if they segregate to the austenite grain boundaries, that reduces the grain boundary energy and makes the boundary less potent to nucleate ferrite or pearlite, because ferrite, pearlite preferentially nucleates at the grain boundaries. So, now if you retard the grain boundary reaction, then what would happen is diffusional transformation becomes, and grain boundaries are also faster diffusion paths. So, diffusional transformations are retarded. So, you find that these transformations are retarded, and you get a separate bay for, which is shown in the left side of the diagram, these are retarded, and you get a separate bay for bainitic transformation exposed, because now diffusional transformation will not happen and you are getting more chance of displacive transformation. You may fast cool, avoid these diagrams, you end up with complete martensite. So, slowing down diffusion pushes the curve to the right, TTT curve increases hardenability of austenite, and faster you cool, you tend to get more chance of formation of this bainite and martensite displacive phases. One difference you may be noticing, that like martensite starting curve is a flat curve, bainite start curve is also shown as a flat curve, flat top curve. Why it is flat top? Why it is not like a C curve here? It is a C curve because it is completely diffusion controlled throughout, right. So, here also if you have to nucleate, you need to rely on diffusion, and diffusion is a time dependent phenomenon. But if you see the original Zinner's work, which is later on published in Badishia's book, you will find the bainite transformation they claim as displacive transformation controlled. So, the first what happens is displacive transformation, which forms the bainite platelet supersaturated with carbon, and then the carbon gets rejected. If there is time, the carbon would end up at the boundary in the austenite at the boundary of the platelet, which is called upper bainite. If time is not there, the carbon will precipitate inside the bainite plate itself, which is called lower bainite. So, because displacive transformation dominates the nucleation, here you see a flat curve like in martensite, because what is required is to activate some defects to form the nuclei, right, and some amount of undercooling is required to activate say 5% defects, which you can consider as the nucleation of bainite or nucleation of martensite. If you cool further to a lower temperature, even 50% defects will now nucleate. Okay? And defects are, if you go by that, as I said, Olsen and Cohen's paper, defects are also dislocation dissociations kind of things. So, some dislocation partials are involved even in the nucleation of this kind of phases. So, so to start this process, nucleate this process, it is a very fast process. So, it is not time dependent, because you cannot, another point is you cannot catch, because there is another theory which says, well, whatever fast the interface can be, still if you have a very high speed camera, you can pick up its movement, right. So, some time dependence is there, which increases when you are using more alloyed steel, because there the transformation front slows down a bit. Okay. So, there are martensitic transformation which is time dependent, shown in the papers, and movies are taken, but since this transformation happens very fast, the interface moves like a zip, you cannot appreciate the effect of the time. So, you only see the effect of temperature, which saturates certain number of nuclei. Okay. If you reduce temperature, more number of nuclei will now activate. So, you will say higher fraction of nucleation. So, that is why bainite top curve is a flat curve like martensite start. Now, according to Badishia, I am completely following Badishia's theory in this respect. There are three types of transformation. One is what he says is diffusional transformation, or we call it reconstructive transformation, or he terms it civilian transformation. Civilian means if there are a number of people are lying in the queue, if you ask them to ride in the bus, they would sit according to their wish. They would prefer to sit with their friends, with their child. So, if you think a child as a carbon atom, small atom, okay, parents are say manganese nickel substitutional atom. So, likewise they will choose their neighbors. There is another way, which is the military. So, they will make a queue and sit along the queue. So, they will not leave their nearest neighbors. So, they will always keep their second person, the battalion, along with them. So, if you ask them to sit, they will sit 1, 2, 3, 4, 5, 6. They make a queue 1, 2, 3, 4, 5, 6, and accordingly they sit. That means there is no partitioning happening. They are not choosing where to go. Whereas civilian, they choose along with their wish both substitutional atom as well as carbon atoms, nitrogen atoms, interstitials. And there is a third category, which he termed that paramilitary transformation, where the parents sitting like a military, but young people who are below 18, they can choose their position. Okay. So, carbon can sit partition according to their wish, but substitutional elements, they follow a particular order, which is typically Widmanstätten ferrite. If you know this transformation, it requires at a time displacive transformation, along with that at the same time carbon diffusion. In the theory of bainite transformation, displacive for the growth, displacive happen first and then carbon gets released, and then again displacive happens. But in Widmanstätten ferrite, both the things happen at a time. Okay. On the other hand, polygonal ferrite, pearlite transformation, it is completely civilian transformation, where all chooses their nearest neighbors, and carbon preferentially are substitutional elements, depending on the dissolution, solubility, they move into austenite. Some elements prefer to move into ferrite, like that. Now, this compositional profile at the interface. So, these straight vertical lines indicate the interface. So, there can be different types of transformation. For example, the top one we see carbon is also almost fully partitioning, right side is austenite, left side is ferrite. Substitutional element is also fully partitioning, and the away substitutional element is written as I, carbon is written as C. So, at a much away from the interface is propagating, you think, and much away the average composition would prevail. So, this is full partitioning, this is near equilibrium, full partitioning, both carbon partitioning as well as substitutional alloying partitioning. Next is called local equilibrium, which now if you increase the driving force, the top thing happens when you are cooling very slowly, forming say polygonal ferrite perlite. If you increase the driving force for transformation, interface velocity increases, then what is happening? Carbon is partitioning. Substitutional elements want to partition, but they are not getting time to enter into the preferential position. So, if they want to go to austenite, they are leaving ferrite, but then remaining piled up at the interface, which we call is non-partitioning local equilibrium. So, they are saturating locally at the boundary, interface boundary. This high temperature austenite to ferrite transformation at a very short time, if you do not allowing time, they will not get time to diffuse, or fast cooling, ferrite perlite transformation, fast cooling, you may tend to see this kind of substitutional transformation. Then there is something called constraint equilibrium, that is called para-equilibrium transformation, where carbon is partitioning, but there is no partitioning of substitutional solute. Okay. So, kind of say Widmanstätten ferrite, where the carbon is completely leaving, because what is the difference between this and para-equilibrium with partial carbon supersaturation? I will try to, there is a small difference between them. More likely is Benedict transformation is that we call it partial carbon supersaturation, para-equilibrium, no partitioning of substitutional solutes, but the carbon content in benite is higher than the carbon content is in polygonal ferrite. Benite can hold, benitic ferrite can hold more carbon. So, carbon is partitioning, but not to an extent which happens in polygonal ferrite. So, that we call partial carbon supersaturation. And then final example, no partitioning at all, neither carbon partitioning nor substitutional partitioning, which we call it martensitic transformation. So, carbon diffuses much faster than iron, that we must need to remember, or any substitutional solute. Diffusion of iron or substitutional solute become rate controlling in that case. Okay. If you depend on substitutional solute diffusion for the transformation to happen, then it has to be slow, your cooling has to be slow, because the interface movement will be decided by the substitutional diffusion or iron diffusion. But if you do not, if your suppose your driving force is so high that transformation you do not have control, it is moving like anything, then there either can be carbon diffusion or no diffusion at all, complete displacive transformation, where the entire thing transforms by a shear and dilation, and all the nearest neighbors are retained. So, it is called solute trapping. So, completely solute is getting trapped. Hardenability I think I have already explained. So, let me come to martensitic transformation. So, austenite, typically what is the shape of martensite or benite? It is a plate shape, right. We call needle, but more correctly if you see in both, if you polish both vertical surface as well as the perpendicular surfaces, you will find it is a plate shape, okay, or small plate we call platelets. So, it is typically we see this is the shape. On the other hand, if you just have a single crystal of austenite and allow its part to transform, you would have seen something like this. This part would have sheared and you need not have to see a thin plate, and this is called the habit plane, that is the interface plane, where which is the interface between transform phase and parent phase. So, where from this plate shape is coming? The plate shape is coming because of the constraint of the surrounding austenite. Here a lot of shape deformation is going on, and it is under the constraint of the surrounding austenite. That is why it cannot bend freely. Here it is distorting freely because it is happening in air, surrounding air, it is not applying any resistance. So, it can shear on its own, it can change its shape, it is called shape deformation. It can happen on its own, there is no constraint, but here the surrounding austenite is applying its constraint. So, when it happens inside an austenite, a small part is transformed, it is formed thin plate, and I will come more into it. Now, there is one very interesting aspect, this habit plane that I said, the interface plane. It is coherent and it is called an irrational plane, which is represented by some irrational, means you cannot represent by integers. Say root 2 is root 2, root 3, 1. It is an irrational plane because you cannot represent it by its integer. So, we try to forcefully explain the plane's Miller indices as in the form of an integer, which can be different, which can be very simple integer depending on the system you are working with, and which can be very, very complex like 31510 or 252 like that. Okay? And still these are not the accurate representation. These are deviated slightly from this. These are most closest integer representation. So, habit planes are called irrational planes. Actually, these are irrational planes. And in general, when a phase transforms in FCC to BCC or BCT, we expect the what kind of relationship, orientation relationship? The closed pack plane would remain parallel, the same, and closed pack direction would remain the same. So, some of these relations are written here. You see the most popular relation that it's followed is, you see the closed pack plane of both these phases are parallel, closed pack directions are parallel. So, it is called Kudrumov-Sachs relation, they have proposed it. Now, first of all, coming to this kind of transformation, what is happening? You have a single crystal of austenite and you are transforming it by shear. So, it is displacive transformation that is happening. So, what is happening is, you to shear there must be a discontinuity, then you are tilting both part, right. This part is there, this part get tilted by shear. So, the discontinuity form, will there be a real discontinuity? No, it will be taken care of by defects like dislocations. Dislocation would come, form an array, and it will take care of the, suppose it is a tilt angle. So, the dislocation edge dislocation array would take care of the tilt angle. So, here we are showing the edge dislocation array. So, at the interface there has to be an edge dislocation array to take care of the shear strain. Now, how the interface would move? The interface has to be mobile. So, all these dislocations lying on the interface should be able to move. So, they have to be glissile. The interface and all the interface dislocations have to be glissile. Then only this part is like this and this part is like this. So, this part would, the interface would move and you will get martensite this side, more and more martensite. Now, to have the interface glissile, whatever lectures and books I have read from Badishia's theory, which he followed from the previous work, the interfacial dislocations, this theory says that has to be a single array of dislocations. So, if it is a single tilt, you can only have a single array of edge dislocation with Burger's vector out of the interface plane, because this interface has to move, right. So, Burger vector cannot lie on the interface plane, dislocation have to move sidewise. So, Burger's vector out of its plane and they have to be mobile, this interface dislocations have to be mobile. So, this mobility can come only when there is a single array of dislocation, say single array of edge dislocation. Okay. Suppose you have a single tilt. If you have a tilt and twist, then who would take care of twist? Then you need a separate set of screw dislocations come to take care of the twist part. Tilt is taken care by an array of edge, twist will be taken care of by a screw, which will create the step along the dislocation line. So, now if you do this, then there would be a problem. What would be the problem? As it moves, this dislocation would intersect with each other. Edge and screw would intersect with each other, and we have learned in the dislocation theory course something called jog. So, jog is a step in the dislocation line that takes the dislocation out of its original plane. So, if I have a plane where there is edge dislocation line, there is screw dislocation line. So, screw dislocation will have a jog. So, part of it will be now out of its interplace plane, and the nature of that jog is often edge type jog. So, if you know about dislocation theory, edge type jog in screw dislocation is highly obstructive, because screw dislocation can cross slip, it is mobile in any way, but edge type jog restricts its movement, because now it can move only one plane where the line and its Burger's vector lie. So, two perpendicular things, line and Burger's vector of edge is perpendicular. So, it can only move like this. So, its mobility is restricted. On the other hand, if you think of edge dislocation, what will happen? At the interface there is edge dislocation. Now part of it formed a jog and moved out. Edge dislocation means Bajaj vector like this. So what would be the nature of the jog? Screw type jog. But if it has to move like this, then the jog has to move along the line, right, along the line length. But we have read that dislocation is not a train. Dislocation cannot move along the line. It always moves sidewise. So a screw type jog cannot move like this. It has to move sidewise. So along the interface, then an edge dislocation with screw type jog also cannot move. So the dislocation line has to be immobile then. So to take care of the single area of edge dislocation, there comes the most important requirement, that one line, the line along the dislocation line vector, has to be invariant. Invariant means there will be no distortion along the line or no rotation along the line. The line length cannot change, the line cannot rotate. So that is the criteria now comes. So for Martin-Side transformation or any displacement transformation, there has to be an invariant line strain, right? A line has to be invariant. With respect to that line, now anything can happen beside that. So now we try to explain in the middle how this kind of shape change happen. So for the time being, let us consider that blue is austenite. Let us consider this base as invariant plane, mind the line and plane. So we are assuming it as the habit plane, invariant plane. So what kind of shape change has to be there? There are two types of shape deformation it has to accommodate. If you transform FCC to BCC, one is you have to do a dilation. Actually you have to expand this 2x and y direction, and there would be a shear. So next slide I will show the bend strain, bend diagram, where there would be a shear and there would be dilation along two axes. Shear along z axis with respect to z axis, compression with respect to z axis, and expansion with respect to xn. So dilation and shear both are involved. So there is a shear strain S, there is a dilation strain delta, and actually in this kind of transformation, although schematics even in Badeshia's book shows exaggerated picture, actually the thing is like this. So the black is austenite, the red is the displaced Martensite plate. Okay. So what it is showing? Shear strain is lot. The shear strain magnitude can be 0.26, which is very, very high, which can even deform the plastically deform the surrounding austenite, right? It's a very big strain. Whereas the dilation strain is very small, rather small. So these blue lines are indicating basically displacement vectors, displacement direction and magnitude, displacement vector. Displacement vector remains almost parallel to the habit plane. So this below plane is the habit plane. It's almost parallel, slightly deviated. Okay. So now if you think, if you make a Martensite plate big, what would happen? Your the magnitude of the displacement has to be large, because if you produce a very thick plate, red, then what is the magnitude of the displacement? Very large. Whereas if you can maintain it very thin at the tip, how much is the displacement? Very, very small. Okay. So at the same amount of shear strain, here shear strain is same in all the points, but shear displacement can be very small if you can make it in a very thin plate shape compared to a very thick box. So in that case, your displacement quantity would be very large, and the elastic strain energy per unit volume is represented by this equation, where delta and S are dilational strain and shear strain respectively. Mu is the shear modulus, and C by R is the aspect ratio of the Martensite plate. So C is the minor axis, R is the major axis direction. So to maintain low E value as per Christian's 1957 work, the calculation is quite difficult. To how we can maintain a small elastic strain energy? by keeping the plate thin. We can work with this aspect ratio. So, typically this aspect ratio remains around 20 times larger length compared to its thickness. Okay? And these calculations are not very difficult. From elastic strain energy, you know the strain energy is half into E into epsilon square. So, here it is not fully elastic. So, half will not be there because the curve would be like this. So, if you take the area under the curve is E into epsilon square. So, from there the displacement term is coming. Okay. So, that is why this plate is very thin. Now, here we are showing the Bain strain diagram, that in FCC you can draw a BCT kind of a structure by joining these points. Okay. So, this is the kind of shear that is involved in as per the Bain's model. If you want to transform FCC to BCT or BCC, here we are showing BCT. Next picture we will show how BCC looks like. So, this is the, so in to convert it to BCC, what you have to do now, you do this shear transformation and then you compress along the z direction and you expand along the x and y direction, which is shown in this slide. So, this is a more accurate kind of slide. You see FCC, inside that this red box is showing kind of BCC. Please apology for my schematic, it should look the same, all the magnitude should be same, which I could not do, but I tried to maintain. Okay, so I tried to maintain the diagonals, the orientation relationship unchanged. Okay, so here you will see z axis remains the same. So, 001 gamma and 001 alpha are the same. Now, what becomes 110 gamma, which is phase diagonal, becomes equal to 100 of alpha, and another phase diagonal becomes 010 of alpha. So, this is the Bain. So, here we are coming into the first orientation relationship, which we call the Bain orientation relationship. Okay. And here you see we have compressed this side and stretched in these two sides. So, this is dilation and there is a shear process involved. So, in doing this, if I ask you which line remains invariant in the left hand side schematic, what is the answer? Is any line remaining invariant? Vertical line shortened, right? Other lines extended. So, none of the lines are invariant. Okay. So, there is no, in Bain model you cannot maintain an invariant line strain. So, it is a kind of approximation, but it is not correct. So, we are moving into more accurate forms. You do this. So, the blue circle is austenite. I am drawing this blue box, suppose FCC in the form of blue circle, right. Now, what I am doing, I am applying a shear strain which deforms it. So, this is the red structure is its deformed version. So, here you see what happens if I take line OA and OB, they change to OA dashed and OB dashed. Okay. OA and OB change to OA dashed and OB dashed, where line length is the same. So, these are same in terms of their length, but what happened? They have rotated. So, there is a rotation, right. So, basically I have compressed it. So, it got stretched and then you see still these two lines are rotated. So, now I have to maintain one line undistorted and unrotated. What I have to do? If I can do this red by tilting, if I tilt now this red oval or rugby ball, and then if I make OA dashed superimposed on OA, then I have the OA line invariant, right. So, that means you need a shear which we call Bain strain plus a lattice invariant rotation. The word is lattice invariant rigid body rotation. So, these two things are required, and that is why Bain relationship is not completely obeying the Martensite orientation relationship, because It is not taking into account the rigid body rotation. Now, if you take the rigid body rotation, here we are showing this rotation. This is the initial case. You now rotate it to make OA fixed, OB rotated further, that we are not bothered about. We are only interested about OA, which remains fixed. So, now so bend strain plus rigid body rotation gives you the right kind of invariant shear required for this kind of transformation. So, expansion is happening. So, bend strain can be calculated. The lattice parameter of austenite if you calculate, the lattice parameter of new transform BCC if you can calculate, it is possible to calculate these strains. So, the Z strain will be compression, high value of compression, and these two would be expansion. From the lattice parameter it is possible to calculate. So, it is called bend strain tensor. Now, comes a more complex problem, because we could not explain 2-3 aspects so far. What we could not explain? We could not explain that there is something called habit plane, right? There is an interface plane and there is an invariant plane. So, this plane exactly remains coherent. If you draw you make a scratch along that plane, you will find that is just changing, but there is no shift in that line, in that scratch. So, it is fully coherent, it is fully invariant plane. The interface plane is not just a line, invariant line, but it is an invariant plane. Okay? Although it satisfies an invariant line because a plane contains a large number of invariant lines. Second thing, we could not explain the irrational habit plane. The previous calculation perfectly explained your structural change and orientation relationship. The orientation relationship, after the rigid body rotation you get the right orientation relationship. But two things you cannot explain. One is the invariant plane, and second thing you cannot explain is the irrational indices of the invariant planes. Okay? Why of the habit plane? Why does that happen? So, there comes a very important theory which is called phenomenological theory of Martin-Celic transformation by Bowles and Mackenzie, and Wessler, Lieberman and Reed at the same time almost they have proposed it. So, if I take this as the ABCD as the austenite single crystal, if I now transform it, right. So, what I have to do? So, AB, I take the AB plane fixed, right, I give a shear. So, I will get now this after shear strain I get this structure. So, that I call the P1 shear movement, homogeneous shear. So, here we end up with right shape, but wrong crystal structure, because transformation not possible by a simple shear deformation. We know that a simple shear cannot give you full transformation, there is a rotation also involved, okay? And it actually give you the wrong crystal structure. So, what you need now, you keep the AD plane now fixed. So, one plane I keep fixed, give a rotation, and then another plane I will now fix and give another rotation, which will make another invariant strain is added, which now shears it, and after the P2 line along A. So, the line along the perpendicular to the A point, that line becomes invariant. So, we have an invariant line now which is satisfying, right. So, we are getting the right kind of structure, but wrong shape, because we are not having also the invariant plane here, because all the planes have changed, AB plane has changed and AD plane also have changed from the beginning to this point. So, there comes a very important theory which says both can be taken care by, if you give a P1 and then that strain is taken care of, this P2 strain is taken care of by lattice invariant shear, twinning, lattice invariant shear in the form of twinning or slip, periodic twinning or slip, right gives you right shape and structure. So, here you see the AB, this is the AB, here also you have the same AB. So, the AB plane now remains invariant, okay, and you get the right shape and the right structure of martensite by this way. Now, why this AB plane becomes irrational? Here you see lot of twin interfaces are formed, which are rational planes. We know what are the twin planes. These inclined planes are also rational planes, but actual habit plane is now an average plane. So, this average plane is somewhere here, right. So, this average plane is an irrational plane, which is drawn by the red line. So, this is how both the aspects are, and this is the example of slip. Twin of course produces interface, and by microscopy people literally see that in the martensite plate either there is twin or there is dislocation slipping at the edges. So, these things really happened, that is proved. Lot of controversial different theories are there. Some theory says that the hard sphere model they take, orientation relationship they take the symmetry, and they say glycine interface may not be required. Whatever happens is the transformation spawn moves, whether dislocation glycine or whether it matters or not. So, different theories are there in Europe and US and Australia. Here also Professor S.B. Singh is an expert in this field, our HOD. So, overall I tried to give you a martensitic transformation. Now, just one slide I tell you about the crystallography. So, Bain relation you have drawn in a single way previously I have drawn, you can draw the same thing by joining points in a different way. So, you see there are 3 possible ways you can draw this BCC inside the FCC. So, there are 3 Bain variants, we call them 3 Bain variants. We already know their orientation relationship, which is written over here. So, there are 3 you have 3 possibilities, right. So, we call this total number of variants is 3. Now, since Bain is not fully obeying, rigid body rotation has to happen. So, more accurate orientation relationships are proposed by Kudrumov-Sachs and Nishiyama-Wasserman. These are also not fully perfect. Actual thing is slightly deviated from them, but their work, particularly Kudrumov-Sachs, we work with steel, which is a high stacking fault material, energy material, which works quite well. So, orientation relationship I have mentioned, there are 4 such plane relations, there are 3 such directional relations on those lying on those planes, and there are for each direction there are 2 twin related variants. Professor Field was talking about twins. So, 60-degree rotation with respect to 111 FCC. So, ultimately it will end up with 60-degree with respect to 110 in BCC. So, if twin variants form, they will be high angle separated boundaries, and Nishiyama-Wasserman does not have the twin variant. So, there are 12 possibilities, 12 variants they say, and this paper nicely explains this. So, what you will find that variants are written like this: V1, V2, V3, V4, V5, V6. In all these cases you will find the plane relationship is the same, which we called closed packed plane or parallel group, CP group. This is CP1. Similarly, from 7 to 12 you will get plane relationship same, planes, parallel planes are the same, directions are changing. So, 7 to 12 you will find different set of directions, 13 to 18 another set of parallel planes which we call CP3. So, 4 possible closed packed groups which generally forms the packets. So, for each closed packed group single planar relationship, but directional relationship can change. Now, you can take their misorientation with respect to the first variant V1. So, if you take V1, V2 is 60-degree oriented. Why? Because they also, you can also match them with the corresponding Bain group, closeness to the Bain group, not perfectly matching, but near the Bain group. One Bain is here, other spot will be satellite spot, KS or NW spots will be near to it. So, it follows close to B1, it follows close to B2, and since they are in different Bain group, their misorientation is high. So, whenever they fall in different Bain groups, you will find misorientation will be high. When they fall same Bain group like V1, V4, V2, V5, V3, V6, they try to form together to have a close misorientation boundary, right. So, together they form a block, and then so V1, V4, V2, V5 like that they arrange. Similar color means slight orientation difference, and they form a packet which is following a CP group, and similar thing is happening between them. But there are, if you apply stress, if you apply strain, then situation can change. Then V1 can form with a twin relationship with V5. Inside austenite there can be twinning when transformation happen. One variant forms and other variant forms in the twin relations. So, there you can have V1, V2, you have a high angle boundary then. So, high angle boundary is typically the area in which we work. We prefer high angle boundaries because they tend to deflect the crack. If a propagating crack is there, high angle boundary is deflected. So, if you can create different high angle variants, then from that point of view it is better. For that, plastic deformation sometimes helps because you create strain, and this strain produces a shear slip also involved because there is a slip plane, there is slip direction. When the variants form, they tend to align their habit plane close to the slip plane. They tend to form their length along the slip direction. So, likewise, if you apply plastic strain, variants may be favored. Some variants you may not get 24 variants. If you get 24, you are very happy because you are getting a random texture which is good for deflecting crack. But if you are deforming plastically, then what can happen? There can be variant selection, which is itself a very big topic. Lot of research is there on this area. So, I tried to give you a glimpse of the entire thing. Let me show you some microstructure at least. If I have not shown you microstructure, so these are the martensite plates, long plates. You will find martensite plate long from one interface to other interface, and then other points nucleate at the edges and grow to the interface. Okay. There can be something called autocatalytic nucleation, that it forms a strain and inside the adjacent austenite, and the strain help in nucleating another variant which takes in front. In bainite you will find a long kind of a region where there will be short platelets. Here you do not see long plates. Why? Because bainite forms when austenite is more plastically deformable, softer. So, in front of a bainite plate, as it grows small, there are a lot of strain accumulated at the interface. So, austenite gets deformed and the dislocations interact with the interfacial dislocations, you know. So, which is called mechanical stabilization, and it will stop the growth. So, now the excess carbon will go out. Now, that from that strain another thing will nucleate, right. So, short platelets, we call it platelets, short platelets will form. So, like here you see short plate, like similar kind of a structure, you look like a long network, but it is made of very small short platelets. So, this is bainite. Okay. Perlite, what is a perlite? Perlite is basically a cabbage perlite nodule. It is nothing but a single nodule is a single crystal cementite forming like a cabbage, and if you dip the cabbage in water, that water is your ferrite matrix. So, that is perlite. If you cut a section, you will see only some leaves like this. So, we call that a colony, some leaves like this, some leaf like this. As you see the section, leaves are oriented in different way. So, whatever is important is interlamellar spacing and the cabbage size is important. If you make a smaller cabbage, it is good for toughness because it deflects, because the cabbage boundary is the high angle boundary. Inside it, the orientation relationship is the same. Okay. There are some other microstructures like Widmanstätten ferrite, which is very important microstructure, which forms by two at a lower driving force displacive transformation happening. So, two plates form self accommodating. One is forming and another is forming along with it, and they two are mutually taking care of their shape strain. So, that austenite need not have to deform much. So, this is the schematic that is showing that. So, that is why these plates are thick and long, preferably nucleate at the boundary, thick and long, and associated with carbon diffusion at the same time when this is happening. So, these are thick long needles. Similarly, there is another microstructure which is called acicular ferrite you may come across. This is called inside the austenite grain the nucleate in the same like benite, but the nucleate in all the different directions. If your austenite grain size is very large, there is grain boundary, less grain boundary area. Benite preferably nucleates at the grain boundary, which is not possible. So, inside if there are inclusions, non-metallic inclusions, they provide a good surface with less interfacial energy, less strain energy, like titanium oxide, titanium nitride, vanadium nitride. So, there this forms, this can grow like a polygonal ferrite, which we call intragranular polygonal ferrite, like vanadium nitride it happens. On the other hand, they may grow like a benite plate, which is called acicular ferrite. All direction they grow, they impinge upon each other. So, we get a variety of orientations, which is good for toughness. In low carbon line pipe steel, this structure is preferred. Another structure, we see benite in the form of grains, because here we are continuous cooling at a slow rate, very low carbon steel. So, the benite platelet you cannot distinguish, they are very low angle boundaries, and the cementite network also it is not forming at the boundaries. So, that is why we tend to see the entire region in optical microscopy like a grain, and instead of cementite network films at the boundaries, they form Ma constituents, because small austenite areas the carbon rejects and they join the austenite areas, which forms martensite austenite constituent. So, granular like benite structure with small Ma islands, which is called granular benite, but in if you do EBST, you will be able to find out the boundaries, low angle boundaries which are separating the platelets. In optical microscopy we cannot, not good for toughness because it is a coat structure. So, I think with this I end. I had lot of slides, but maybe 1 more hour is needed. I have prepared too much for this. So, thank you. Oh yeah, I have, my content was very much, sorry. Yes, so I am thankful to Professor Somjit Biswas and Professor Shampaij, because I generally do not teach this subject, but they made me speak on this topic. So, I had to thank you. Professor Field also.
Voice is enough loud. Yes. So far nobody explained these things with an example of cabbage. So that was really nice.
No, that's not mine. I have taken from Badishia's work. So
that.
I have already,
yeah. So I'm sure that students also enjoy that. I mean, it is very easy to understand if you give that type of example.
It's not a sandwich. Yeah.
No, but you have drawn cabbage and the leaves.
Right. It's a cabbage. It's not a sandwich. That's the point.
So, it was a very nice presentation, and it actually made me nostalgic, because I was reading a lot about these things in around 2010 and at that time, and everything become totally fresh. So, I would ask Professor Field to give this small gift to Professor Devalaya Chakravarti, and so there is a small like a breakfast outside, so we can go and grab it and have it if we want, keep it if we want. So we can grab that, and yes, you can ask questions, but I didn't give you time to ask questions because it's already, we are ahead of the session.
Yes,
so
you please send me the questions to Professor Biswas, and I think that will be very, I will send you a written answer, okay? Because I also have class, I am sorry.
Yeah, তোমার ক্লাস আছে তো, তোমার শুরু হয়ে গেছে ক্লাস।
তুমি কোশ্চেনগুলো
ওকে, ভেতরে স্পিকার অন নেই, বাইরে মানে তোমাদের রুমের স্পিকার অন আছে। হ্যাঁ, নাও ইট ইজ অন। So, good morning. This is the third talk of this session, and the talk is basically related to what are special grain boundaries or what are coincident site lattice grain boundaries. Okay. Now, one comment I received that too much food. It's been given to you so that you become lazy and be seated at your position, so that you could not move anywhere. I hope that you have had a nice breakfast now. So, I would like to invite Professor Sumantra Mandal, and I hope that for you guys, he doesn't need any introduction. So, he is faculty in metallurgical and materials engineering, our department in IIT Kharagpur, and he works in grain boundaries and interfaces, and he has a lot of very important publications in this area. He also works with corrosion and surface property of materials and relates it to texture and grain boundaries. So, welcome. I would like to welcome Professor. Please take the stage.
Second. Yeah. Okay, thank you very much, Shamjit, for the nice introduction, and thank you very much for giving this opportunity to speak here. So, I'll be talking on coincident side lattice boundary and its implication, and mainly I will be focusing on grain boundary engineering and its implication on material properties like corrosion. So, you know that majorities of engineering materials are used in polycrystalline form, right? And their performance is linked with the boundaries, and the boundaries can be categorized low angle boundaries or high angle boundaries. It's very basic definitions, right? I'm sure you have read this in your undergrad course. Mesh orientation angle, theta less than 15 degree, less than equal to 15 degree low angle boundaries, and those having more than 15 degrees high angle boundaries, right? And all of you know that high angle boundaries give you strength, typical Hall pitch relationship, everybody knows. So, grain boundaries are beneficial because it gives you strength, but there is various degradation phenomena happens on the boundaries, like fracture, corrosions, cavitations, segregations, right? So, if I want to tailor microstructure employing grain boundaries, I want to have the beneficial properties of grain boundaries like strength, and at the same time can we minimize this kind of intergranular degradation phenomena, right? So, apart from low angle and high angle boundaries, in the high angle boundaries categories there is one type of boundary which is known as coincident side lattice boundaries, right, CSL boundaries. And particularly I will show you as we proceed these CSL boundaries, particularly those CSL boundaries value are low, we will come to that. They have certain important properties in terms of energy. I will come to that, but let us recap few basic thing on the grain boundaries. So this is a typical picture of low angle boundary, high angle boundary. As you know that low angle boundary can be, the mesh orientation between low angle boundaries can be accommodated by means of introducing dislocations, right. High angle boundaries, this mesh orientation cannot be accommodated by introducing dislocation, that is why there are various broken bonds, and this is the reason why the energy of the high angle boundaries are typically high as compared to low angle boundary. Now when I tell energy are high, this is basically a very simplistic approach. There are many other parameters which may affect the energy apart from the mesh orientation angle. Those things we will not go into detail because then we have to consider the grain boundary plane and all those things. Today's discussion will mainly focus on the mesh orientation, because coincident side lattice boundary or CSL boundaries concept is based on the mesh orientation alone, it does not consider the grain boundary plane. So this will be of course a simplistic assumption, and some of you probably know that grain boundaries have 5 degrees of freedom, 3 comes from the mesh orientation and 2 comes from the plane. So while talking about CSL boundaries, we ignore the remaining 2 degrees of freedom which comes from plane, and we only consider the mesh orientation, and thereby we take care about only 3 degrees of freedom, right. So this thing, while talking about CSL based grain boundary engineering, we have to keep this thing in our mind that this is a simplistic approach, right, and of course there will be some limitation on that. Okay. So let us discuss what is CSL boundary, right. All of you probably have heard that the mesh orientation, what is the meaning of this mesh orientation angle? So a simple schematic diagram I want to show you. Suppose this is one crystal and this is another crystal, or this is one grain and this is another grain, right. So these 2 grain, as you can see that orientation difference between these 2 grain can be expressed in terms of one angle and one axis. If you rotate 50 degree along 001 common axis, then what happens? These 2 crystal merged with each other and there is no orientation difference, right. So that means this is the meaning of your orientation angle, orientation angle or orientation axis. When we talk about the grain, we call it as orientation angle and axis, and when we talk about the boundary, we call it as a mesh orientation, right. So this is the meaning of mesh orientation angle and axis, and the CSL concept come, probably I will first show you a typical schematic representation. Just one second, probably I have to go there, yeah. So this one which will give you a little bit more idea. Is it moving? Yeah. So here I have a 2 crystal which superimposed on each other, right. So I have so right now they are not visible because they are superimposed. Now if I rotate, so right now they do not have any mesh orientation because there is no angular difference between them. Now let us rotate one crystal with respect to other along this z axis, okay, and let us see what we get. Yeah. So as you can see, now we have created a very small orientation difference, right, and let us slowly increase the orientation difference as we proceed. Just note down this highlighted to lattice point. Just see here, this angle is 36.9 degree. Once you rotate one crystal with respect to another along the z axis, which is 001 typically, you can see that there is certain periodicity you can find out here. Consider any of the lattice, either blue lattice or red lattice, and see the periodicity. Anybody can figure out what is the periodicity? Periodicity means out of how many atoms both the atom is coincident. Coincident means superimposing one above another. Just see the periodicity. For example, consider the red lattice. Start from here. So this is not working here. So this one you just consider, right? So there it is superimposed point, and you go along the red lattice. You see first, second, third, fourth, fifth. Fifth atom is the coincident. Similarly, if you take the blue lattice, for example, start here, where I will start, maybe here, right? First, second, third, fourth, fifth. First, second, third, fourth, fifth. Every fifth atom of the blue is also coincident. So whether you take red lattice or blue lattice, every fifth atom is the coincident, right? So this we call a sigma 5 boundary, because out of every fifth atom, one atom is coincident. Is it clear? I hope it is clear. So coincident side lattice means there is certain atomic matching, right? And as a result, since there is atomic matching, what is the implication on that? The number of broken bonds are less. For example, sigma 3, this is sigma 5, sigma 3 what will be? Out of 3 atom, 1 atom is coincident. Obviously, if the number goes down, that will be better in terms of periodicity, in terms of broken bond is less. Sigma 1 means every atom is coincident, right? And as you go high, the number of coincidence atom will decreases, and obviously what will happen? The number of broken bonds will increase and energy will increase. So typically one can expect that if you have a lower periodicity, if you have a higher periodicity means lower CSL number, then you will have a less number of broken bonds. Less number of broken bond means what? More stable, lesser energy, and we can expect this kind of boundaries will give you better resistance against interfacial degradation phenomena. But again I am telling these are very simplistic assumption, because we are losing another 2 degrees of freedom related to plane. We are only considering the misorientation, right? Okay, so with this, let us go to again. Yeah, so in 2D this is sigma 5, whatever I showed, the same thing here, shown here. Okay, now coincidence. What is coincidence? This picture will tell you coincidence. So it's possible, right? Nah? Somebody may tell 36.9 degree. What is coincidence? It's possible, right? And I was reading one book by our famous Satyajit Ray, and there I found this coincidence. Okay, so quickly go through. You know, Lincoln and Kennedy, they have similarities. They have 7 characters. One became president in 1860, another is 1960. Both were assassinated on Friday, accompanied by wife, inside a theater named Ford, that was inside a car made by Ford. Next president was Andrew Johnson, next president was Lyndon Johnson. One was born on 1808, another was 1908. Lincoln was assassinated by John Wilkes Booth, 15 characters. Kennedy was assassinated by Lee Harvey Oswald, 15 characters. And they were born, one was born 1839, another was 1939. So coincidence is possible, right? So it is also possible in crystal, it is also possible in material science. Okay. So now hopefully it is very clear to all of you that one crystal has to be oriented in a certain angle and axis, then only you will get this coincidence, right? So these are the angle and axis combination that is available in any classical textbook, you will find that. So 3, 5, 7. One important thing you are seeing that your CSL boundaries are always odd, right? And as you can see that they have particular angle and particular axis, right. So typically we are more interested about low sigma CSL. Now low means what? Up to what value? As you can see that one can go 35, 37, 39 like that, 83, 85, 101, you can have so many CSL, but does they have any meaning as far as the special property is concerned? No, because then periodicity will be very, very less, right. Now out of 100 one atom is coincidence, what is the implication, right. So considering this, up to sigma 29 people have seen in the literature, they have found, they have done on many experiments on many materials, and they have observed that up to 29 it makes sense, right. So that is why if you see any classical textbook, they will mention that low sigma CSL boundaries, special boundaries, so many acronyms are there up to sigma 29, right. Now again this value whatever I was showing in the chart, for example 60 degree along 111 axis, if both the crystal are misoriented, then only they will show out of 3 atom 1 atom will be coincident and this will be sigma 3 boundaries. But then really 60 degree exact, is it possible? What will be, no, coincidence is possible, but then if I want to get frequently in my material, okay, does it make sense? It does not make sense. And please remember, these are considering simple hard sphere model, right. But in real material you have dislocations. In real materials you always have dislocations. Whatever the animation I show, that's only atoms I showed right now, but in real materials you will have a dislocation. So in that case, this dislocation will also play a little bit role. For example, low angle boundary. What is the definition of low angle boundary? Up to 15 degree we consider. Why 15 degree? Why not 2 degree? Why not 5 degree? Because it has been seen that this deviation up to 15 degree you can adjust it by dislocations, and these are called primary intrinsic grain boundary dislocations. Primary intrinsic grain boundary dislocations. Okay. Now similar kind of concept can be introduced here also. Similar kind of concept can be introduced here also if there are certain deviation. For example, say instead of 60 degree you have 62 degree or 63 degree along one axis. Can it be coincident? Can we consider it is coincident, or it is a normal boundary? By the way, sometime I will tell random boundaries. What is the meaning of random boundaries? Random boundaries means those boundaries which are high angle boundaries and not special CSL boundaries. Special means up to sigma 29, let us consider for the time being. Okay. So if it is misoriented by 63 degree along one axis, can we consider it's a CSL boundary or random boundary? What should we consider? Because please remember, as I said, you have what? Dislocations. So there are postulation, there are criteria which gives you to calculate the deviation from ideal CSL misorientation. So there are two well recognized criteria. One is Brandon criteria, this is very old, but very well accepted. Palm-Bosch criteria, it's a relatively new one. New means not in the previous century. Those things, this has been CSL theory, it's very, very old theory. It's not that suddenly it has come. Probably the first paper it was 1949. Why CSL comes into the picture? Why this grain boundary engineering, all this thing interface? Because after the invent of EBSD, you can routinely calculate the grain boundary character experimentally. You can link with the properties, and that's why it has become, more and more well researched area, right. So if you see this Brandon criteria and Palm-Bosch criteria, obviously which one is more restrictive? Restrictive you understand, right, which will allow less deviation. Obviously the second one, right. And by the way, what is the meaning of this? This is the deviation, maximum deviation, how much one can allow to consider a boundary, a particular CSL boundary from their ideal misorientation, and this is basically a proportionality constant. How you will find out the value of this constant? Just put the value of sigma as 1. If you put the value of sigma 1, What is the meaning of sigma 1? Low angle boundary, right, where every atom we consider as a coincident. And what is the maximum deviation for low angle boundary? We can consider up to 15 degree. So if we, to find out the value of this proportionality constant, put the value sigma as 1, what will be the value? This will be 15 degree. So sigma naught is nothing but this, this you can consider nu naught is nothing but 15 degree. So this proportionality value will be 15 degree. So you know the now equation, this is equal to 15 degree sigma to the power minus half. For any boundary for sigma 3, put the value sigma is 3 and calculate. So it will be 15 into 3 to the power minus half. What will be the value? Approximately 8.69 degree. So that is the amount of deviation you can allow, 8.67 exactly. So one can calculate the deviation, right, and these are all available in EBSD database. So you don't have to do EBSD software, you know, they will routinely calculate this and give you, but of course you should know the background and basics behind that, what is the relevance of this deviation angle from the ideal mesh orientation. Is it clear? Up to any point of time, if you have any difficulties, feel free to, you know, ask your queries. Okay. So now, once it is known to us the basic theories, let us move to the boundary energy, because ultimately we are interested about the properties, and if I want to understand the properties, we have to understand the grain boundary energy dependence on the CSL boundaries. So as you can see that when I have a CSL boundary like sigma 3, sigma 11, sigma 9 or sigma 5, they have lower energy. So these are, you know, trained as a function of, you know, boundary energy versus mesh orientation angle, and whenever it satisfied the CSL criteria, those were marked as sigma, right. And you can see that more or less these sigma boundaries have lower energies. The striking observation that one should make here, which boundary have the lowest energy? Sigma 3, right. It's not 0 by the way, it's very less, approximately 15 to 20 millijoule per meter square or so on. So its typical boundaries have, you know, 800, 1000 millijoule per meter square, and this is 15 to 20. So you can understand 40 times less. So when you have this lower energy, definitely one can expect those boundaries, if you have more number of those boundaries in your microstructure, it will give you better properties, right. So sigma 3 boundary is the most desirable one, right. So this is the thing, and yeah, please.
Like in previous slide, there were 2 sigma 3 boundaries in the left one.
Yeah, this one. Why? What is the meaning of this sigma? Why we are showing 70 degree and why we are showing again 90 degree, right? That's what your question, probably. Yeah, the reason is, you know, in a cubic system, these are all cubic system. In a cubic system, you have 24 crystallographically equivalent solution, 24 crystallographically equivalent solution, right. So that means any orientation or any mesh orientation can be expressed in 24 different way, but they are same boundary, because of the symmetry, you can represent by 24 combination of mesh orientation angle and axis. For example, simple, just go back there. So for example, this one, obviously you can rotate along, you know, 50 degree one direction, another direction 130, right now. But it is not so simplistic. It's not only about one axis, you can have many equivalent axes. For example, sigma 3, you can get sigma 3 boundary along 1 axis, 1 axis if you rotate 60 degree. Same to crystal, if you rotate along 110 axis around 70.5 degree, then also you will get sigma 3 boundaries. So what does it mean? Because of the symmetry, you can get the same boundary by different combination of angle and axis. So here this sigma 3 boundary, I think this is along which axis they have given, 110 axis. So in 110 axis, along 110 axis, 2 mesh orientation angle is possible for the sigma 3. One is 70.5 degree and another will be approximately 90 or so. 90 or exactly value I don't remember, it looks like 90 or 92 or something like that. And this is possible to calculate. There is one law given by Ranganathan, Professor Ranganathan. So, you can calculate those angle and axis combinations by using those equations. Is it clear? Yeah, please. Yes. So, I purposely did not discuss this because then your plane will come into the picture here. You can see that sigma 3, both are sigma 3, but they have a contrasting energy. Both have, out of 3 atom, 1 atom is coincident, but then both should have lower energy. But then why? Because they can lie on different grain boundary plane. Okay. So, that is why I told that these are some assumptions. We are missing some of the important parameters, important degrees of freedom, but by and large it gives you, at least in both the cases, you can find out the energy is lower as compared to random high angle boundaries. Okay. Typically sigma 3 boundary, as I proceed, I will introduce the concept what is sigma 3 basically, right. So, I will come to that. Okay. So, now let us come to the approach of grain boundary engineering. Okay. So, again this is, as you can see that paper, this is a classic paper by Watanabe taken way back 1983. So, 1993 I guess. So, the concept was introduced long back, right, and the work is going on, right. As I said, after invent of EBSD, routinely people are now doing, and they are introducing the more complexity, as like now people are considering on grain boundary plane and other things, many things, right. So, these are very, very basic concept that I am showing you here for your understanding. Okay. So, considering a typical microstructure here, right, and I can have two kind of situations. So, this is on the surface of the, consider this is my specimen and it is exposed. So, on the surface it can be a crack can nucleate, or maybe your corrosion fluid may be present. So, what will happen? This fluid or crack, what they will try? They will try to percolate. It is called percolation, fluid percolation or crack percolations, whatever, crack propagation we call, not percolation. But if I have something like path here, R means random boundary, and already I told what is the meaning of random boundary. So, if I have a continuously connected random boundaries, what will happen? The crack can easily propagate, or your corrosion fluid can easily percolate. But if this R is replaced by sigma boundary, means special CSL boundary, particularly sigma 3 or something like that, and L means low angle boundary. So, if you have in a path either sigma 3 means sigma boundaries or low angle boundaries, then what will happen? It will be arrested. They will not be able to propagate because their energy is low, they are more compact boundaries, right. So, what we have to have, if I want to manipulate my microstructure by grain boundary engineering, what I have to do? I have to break this connectivity first of all, and second thing, first thing is, first of all I have to increase the number of these special boundaries, and second thing is I have to distribute them so that this kind of continuous connected boundaries are, continuous connected path of the boundaries are not available. So, grain boundary engineering approach relies on these two factors. Okay. So, now suppose in a material you have a limited number of sigma 3 boundaries or sigma 9 boundaries or special CSL boundaries, how you can tailor a microstructure with more number of CSL boundaries. You start with maybe 10% CSL boundary, 20% CSL boundary, and I want to make it like most of the boundaries, like 50% boundaries or 60% boundaries I want to be CSL boundaries, low sigma CSL. How you will get it? So, these CSL boundaries, they show some kind of special behavior, and this comes from the crystallography geometry, right. It is purely geometrical. They share a common misorientation axis, the sum of the two misorientation angles gives the third, and the product or quotient of two sigma value gives the third. Like if this thing, again I am telling in terms of some boundaries like sigma 3, if I have a sigma 3 and sigma 3, they will give you, if they meet, the third boundary invariably will be sigma 9. Okay. Again sigma 9 and sigma 3, if they meet, they will be sigma 27 and so on. So, sigma 5, sigma 3, if they meet, they will be sigma 15. So, like that, this kind of typical triple junction rules they follow. So, that means somehow if you allow your microstructure the sigma 3 boundaries to interact, that means create a situation in your material so that the boundary migrate. You know what is the grain boundary migration, right? Like in high temperature, boundary migrates, provided that in the material you have certain energies. So what will happen? If you allow the boundary to migrate, this boundary can interact, and then in that process what can happen? You can have more number of CSL boundary. So as you can see that in that process, sigma 3, sigma 3, sigma 9, sigma 9, sigma 3, sigma 27, and again this rule sigma A into sigma B, it can be sigma A by B also. So sigma 3, sigma 9, it can also have a sigma 3. So that means you are regenerating sigma 3. So that's why it is called sigma 3 regeneration mechanisms. And most of the low stacking for energy materials, like low to medium stacking for energy materials like austenitic steel, nickel based superalloys, copper, all those things, they show lot of sigma 3 boundaries. So I just want to tell you sigma 3 boundary is nothing but twin boundaries, annealing twin boundaries. You know what is annealing twin, right? So annealing twin boundary, actually if you see the misorientation angle and axis and coincidence, they are basically nothing but sigma 3 boundaries. So in low SFP material you can have, certain sigma 3 boundaries to start with, and if you do some kind of processing, you can regenerate sigma 3 boundary in a material, in a microstructure, which will lead to more number of sigma 3 boundaries, and eventually you can design or tailor a microstructure employing this grain boundary engineering approach. Is it okay? So now, yeah, so these are certain data available in the literature. You can see that in low stacking for energy materials, if I consider up to 29, so they have shown the distribution of CSL boundary up to sigma 29 starting from 3, and as you can see that majority of the boundary is what? Sigma 3, and when you have sigma 3, they can interact and can produce sigma 9 also, and sigma 9, sigma 3 can sigma 27 also. So most of the boundaries in this low stacking for energy material, they are either sigma 3 or sigma 9 or sigma 27, and this comes from the simple crystallographic constraint rule, right? So that is the reason why now onwards I will mainly tell about when I am talking about special boundaries. These are sigma 3, sigma 9 or sigma 27. Okay. Okay, so there are different approaches people have tried, the researchers have tried in the in the past, and I have just tried to summarize. There are many other approaches, but if you see out of all this approach, thermomechanical processing, rapid solidification annealing, laser surface melting, magnetic annealing treatment, mechanical stresses during annealing. So there are different approaches, but thermomechanical processing is definitely the one which most of us we employ in our material, right? Because thermomechanical processing has to be done in most of the cases until and unless you are forced to use cast structure. So if that is the case, then why not to use thermomechanical processing is one of the important route to design your microstructure. So there are different thermomechanical processing route people have adopted, but they can be broadly classified in two different categories: strain annealing or strain recrystallization. Typically, the process is same, you give deformation and then anneal, but what is your extent of deformation, what is your temperature, what is your time that you are adopting. So considering all those variables, you can classify them either strain annealing or strain recrystallization. And these are complex, sometimes empirical, because you have so many parameters to fine tune, right? The material properties, particularly stacking for energies, what is your starting microstructure, whether in the starting microstructure itself you have some good amount of CSL boundaries, because finally what your initiation point is what is your starting microstructure, right? If starting microstructure you don't have CSL, then how you will regenerate it. Mode of deformation, whether you are doing tensile, compressive, shear, annealing time, temperature, number of processing, means how many iterations you are employing. So many parameters are there. And so strain annealing, basically low level of deformations one apply, typically less than 6%, and then some long annealing duration. But these are often difficult to implement, because long annealing time may need to production cost, but then it has advantage, because small deformation one can easily accommodate. So industrially it is most viable, because please remember, this kind of typical processing or typical treatment, when you have to give towards the end, when your component is almost ready, right? Because finally what you want, the end microstructure should have your CSL boundaries, right? Strain recrystallization, typically higher deformation, but again its annealing time requirement is less, so industrially it's cost effective, but again 30% or so deformation, so you have to fine tune, your approach. So we have done some work on this. I am not going through detail about the processing, because the processing route, the concept is very simple. You apply deformation and do annealing, so that you introduce certain instability in your microstructure, allow the boundaries to migrate, and in that process allow the sigma 3 to interact and produce more and more sigma 3 boundary and distribute them in the material, so that what happens, the connectivity of the grain boundaries, random boundaries is broken. So that is the simple concept. So I am not going through this, but I will show you some important implication on corrosion properties, okay, which maybe you are interested to see. So this is starting microstructure, and as you can see that after processing, so starting it was around 40% of CSL boundary, but as we deform and we fine tune the parameter, the final microstructure have almost 60% of CSL and about 60% of sigma 3 and about 13%, 8 plus 5%, so about 13% of sigma 9 and sigma 27. So almost 70% of the boundaries are CSL boundaries, right, low sigma CSL boundaries. So you can see, so this is our work, probably sometimes back we did, and then you can see that these red boundaries are sigma 3 boundaries, blue boundaries are sigma 9, and green boundaries are sigma 27. So you can see that how well they are distributed. Random boundaries are shown in black color, so you can see that random boundaries connectivity has been completely broken. So when you have this kind of microstructure, you expect that they will perform better in terms of any kind of degradation phenomena, because finally percolations you will be able to arrest those, right. So this is the typical mechanism proposed by Randall long back, this one. So where they told that sigma 3 interact with sigma 3 and form sigma 9, and when you can see that this is one grain and this is another grain, right, sigma 3 of one grain interact with sigma 3 of another grain and produce sigma 9, and then again they interact, produce sigma 27 boundaries. But later on people found that there are a lot of issues with this model, because crystallographically it is not robustly designed, means it's the probability of sigma 3 interact from one grain with another grain, its probability is very, very less. So although it is appeared to be correct, but crystallographically it is not very sound, okay. So then I will come to that. We propose a little bit modification of these regenerative mechanisms, and we showed that, I will come to that. So how to quantitatively analyze the grain boundary network, this is another important area where one should know, because finally if you have a GB microstructure, how do you know that you have realized a GB microstructure? Because visually it may appear, okay, I have a lot of CSL boundaries, a lot of sigma 3 boundaries, but how well distributed they are in the microstructure, because it's the distribution of sigma 3 boundaries, sigma 9 boundaries is also very important, right. So then one can see different parameter like triple junction criteria, where J0, J1, J3 you can understand if you see the schematic. J0 means all boundaries are in the triple junction, all boundaries are random. J1 means one boundary is sigma, another two boundaries are random, and J3 means all are sigma. So obviously if you have in your microstructure more number of J2 and J3, the microstructure is good, beneficial. One can do twin related domain, means what is the meaning of twin related domain? In a domain, I will come to the picture probably, let me show you the picture first, yeah. So this is basically a twin related domain. So you can see in this, this is a one twin related domain. In this domain, all boundaries are either sigma 3, sigma 9 or sigma 27. In the entire domain, all boundaries are either sigma 3, sigma 9 or sigma 27. So if your domain size is big, that means what? That means that is good, right? Na? So twin related domain is also another important parameter one can think. And then another important thing is the fractal dimension. Fractal dimension one can calculate, and this the fractal dimension, if it is less, then also it is good. That means fractal means fragmented. More and more it is fragmented, it is better, right? So this kind of analysis one can do, and then obviously if you see, this is a typical iterative process where we have started with as we see microstructure, you can see we have certain number of sigma 3 boundaries, but I have a lot of high angle boundaries continuously connected. As we process, then finally from here you see here TRD size, twin related domain size is very small. Your twin related domain size is very small, but when we realize the GB microstructure, I have hardly 3 or 4 TRD, twin related domain. And then we propose a mechanisms here, unlike what it was proposed earlier. So it's basically you see this one, it will be more clear. So this is your original boundary, this is your original boundary, and what happens when you give instability, when you deform and then anneal, these boundaries migrate, these boundaries migrate, and behind these migrating boundaries you have twin boundaries, right? So for example, behind this, suppose this boundary is migrating, this boundary is migrating, I have so many twins behind these migrating boundaries. These twin boundaries, in that process what happens, they interact. So you can see that this two boundary, okay, so this two boundary, this boundary and this boundary, they can interact. As this boundary process, as this boundary moves, this boundary, they can interact and produce a sigma 9 boundary, right? And so on, that process, the chain reactions continues, and in that process what happens, your TRD size increases, small TRDs are vanished and large TRDs are grows, right? So this is the proposition that what we made. Now I will just show you implications of this grain boundary engineering on corrosion. Two different type of corrosions I will show. One is sensitization and another is pitting. So just to compare, we have taken simple austenitic stainless steel, 304, but please remember here carbon was low, it is not that 304 high carbon, 304L, and even 304L you have a sensitization. Normally we know that if you reduce carbon, sensitization will be less, it will be less, but still you have. So what we have taken 304 SA means solution annealed without any GB kind of treatment, and so the second one, after thermomechanical processing we have optimized the microstructure, and this is my GB microstructure. As you can see that these are only random high angle boundaries are shown, random boundaries, that means these boundaries are detrimental. If I have a connected random boundaries, these are not good, because then corrosion or any other kind of phenomena will be happening very easily. This is my GB microstructure, you can see that boundaries are fragmented. This is TRD map, you can compare the TRD size, TRD means twin related domain size. You can see the contrasting behavior between both the microstructure, and fractal dimension also we have calculated. As you can see that fractal for 304L starting microstructure is very high, and the GB microstructure fractal dimension is very less. So those who are interested about fractal calculations, you can do it, very simple, it is not at all difficult. So this is, you can extract this data from your EBSD map, right? This all are available from your EBSD map. You can extract the random high angle boundary map from the EBSD, right? And from this random high angle boundary map, what you have to find out, maximum random boundary connected length. What is the meaning of that? See, this is your random boundary map, right? All of them are not detrimental. If you have a fragmented, then not a problem. What is more detrimental? More detrimental is if you have a continuously connected random boundary, and that length is very, very dangerous. So we want as minimum as possible that length, right? So what you have to pick out from this random boundary map, you have picked out the continuously connected random boundaries. So here you see this many boundaries are continuously connected, but here only this length is continuously connected. You understand? So once you do that, now you calculate the fractal dimension, and then you can find out what is the value 1.71, 1.427, right. So this is also a good indicator how efficient your microstructure is, right. Now once you have this data, what you can do, you can now do the corrosion test. So we have done the corrosion test. This is typical sensitization curve one can see in a material. These are expressed in terms of degree of sensitization, DOS, right. So what you have to do, simply you have to perform a test in your potentiostat using certain electrolyte, and then you have a two loop. This is forward loop and the reverse loop, okay. So one is called anodic loop, another is reactivation loop. Find out the maximum current in both the loops. For example, in the forward loop this is the maximum current, and this is the backward loop, it is the reactivation loop, this is the current, and you take the ratio, okay. This is your degree of sensitization. Obviously if it is sensitized material, the reverse current will be more. If it is less sensitized, the reverse current will be less. So degree of sensitization means this ratio by this ratio. So obviously if my curve is like this, less sensitized, right. So we have done this, and these are GB material and non-GB material. You can see that even 304L, these are all carbides, like chromium carbide precipitates, sensitized boundaries, and we have calculated. So you can see that degree of sensitization is 17, the value which is heavily almost mildly sensitized, mild to heavy, and this is almost negligible sensitization value. We have also calculated the corrosion rate by, not from the here, we have done aqueous corrosion test. So after aqueous corrosion test, so this is as per standard practice B, it is called. Those who are familiar with corrosion, there are various practices one can adopt. So this is practice B we have adopted, and then this is up to 120 hour we have done corrosion test in ferric sulfate sulfuric acid solution, both the material 304L non-GB and GB, and at different interval we have taken it out, and then we have measured the corrosion rate as well as the microstructure. I do not have to tell you the value, you see the microstructure, you will find out the difference, right. So there are here almost you can see now this is a big TRD domain, right, these are big TRD domain. So it's pretty obvious that within this TRD domain nothing is happening, because all the boundaries are either sigma 3, sigma 9 or sigma 27. But here I have so much continuously connected random boundaries which has given me a severe kind of sensitization and corrosion, right. So grains are coming out because of corrosion. Yeah, and one can see the cross section SEM view. These are surface, right, these are on the surface and these are on the cross section, and how much is your percolation, means how much fluid has gone and damaged your material, that also you can see by cross section SEM. So this is 82 micron, this is 23, even 23 is locally, right, here almost entirely it has, you cannot completely make it your material absolutely bulletproof, no, it is not possible, right, somewhere you have certain boundaries, but you see the overall damages, so very less, right. Okay, so final one, so final one is the implication of GB on pitting corrosion. As you all know that these austenitic stainless steel are very prone to pitting. So we have done pitting on the same 304, it is on 304, it is not 304L, it is 304, and we have done on two different material, one is SA that is without GB and another is GB, and you can see the there are so many parameters here, I think I do not have much time to elaborate on this, but I want to just emphasize on two parameter, one is E pit at potential where your pitting start, and E protection below which the material is not at all pit will not at all form, and in between E pit and E protection what will happen, the pits will, new pits will not form, but already old pits which were already formed they will still grow, okay. So these are the two parameters, obviously E pit and E protection should be as high as possible, if E pit is more or E protection is more, the material is more resistant to pitting. So we have done that, and find out E-pit, E-productions, obviously you can see that the differences. We have calculated the pit growth rate and pit stability product. All of these parameters are significantly low as compared to the solution and material. So this gives you an idea that pitting corrosion resistance also can be significantly improved by grain boundary engineering. And just see this picture, these pits you can visible, right now you can see the pits. And what we have done ACM and EBSD in the same locations. Try to find out where pits nucleate, which are the boundaries which are more prone to pits. You can see this random high angle boundaries are shown in yellow color, sigma 3 red, sigma 9 blue, sigma 27 green, and please find out where the pits nucleates mainly. Yeah, here it is random boundary, triple junction on the random boundary, right. So either on random boundaries or triple junction like J0 type of triple junctions where your random boundaries meets. So that means your random boundaries and the triple junctions, J0 type of triple junctions are more prone to pits. So evidently if you in a material, if you replace those boundaries or replace those triple junctions with J2 or J3, means where either 2 CSL or 3 CSLs like sigma 3, sigma 3, sigma 9 junctions or sigma 3, sigma 9, sigma 20 junctions, then obviously the pitting resistance will increase. Okay, so with this I think I am on time, yeah. So thank you. If you have any doubts, please ask me. I think both the microphone they cannot run together, or you can sit.
No. So it was an excellent presentation and very relevant one. So the floor is open for discussion, so you can ask question actually. Started. Anyone? Yes.
Yeah.
So hello sir, I have only one particular question. What
Yeah.
about this grain boundary engineering evolution during the hot deformation of FCC materials?
Yes. So yeah, in hot deformation, the microstructure, the starting microstructure, whatever we have shown, na? Yeah. I think some. You can switch off. Yeah. The hot deform microstructure also showed some kind of sigma 3 boundaries, because hot deformation also will lead to the formation of annealing twins. But problem with hot deformation alone, that all these twins whatever you are seeing, they are typically within the grain and we call them as neutral twins. Okay. So how? Okay. So yeah. Just see a typical microstructure and please see there. Yeah. See this. When in this microstructure also have a lot of twins, lot of sigma 3 boundaries, but they belongs to a part of within the grain and they don't participate in the network, right. So by hot deformation you can definitely produce lot of sigma 3 boundaries, but their presence are not sufficient. You have to finally distribute them in such a way that the connectivity of the random boundaries is broken. They do not contribute much to the connectivity breakdown right now. So that's why you need to invariably do cold deformation and annealing, so that basically strain induced boundary migration happens and the kind of interaction between sigma 3 or sigma 3 sigma 9 happens, and you can distribute them throughout the microstructure so that overall connectivity is broken.
So second question is regarding what is the future of grain boundary engineering in BCC materials?
Yeah, the future is not very bright. Yeah. So the reason is, what is the practical difficulty? The practical difficulty in BCC material, sigma 13 boundaries many people have reported, right? I mean, if you see, there are not very high number, but there are reports. But you cannot increase that proportion like the way we are doing in the FCC material. Finally, it's like a business. You have to invest something and then it should not stay there, right? Now it should multiply. So in FCC material, the sigma 3 regeneration mechanisms operates, right? Sigma 13 boundaries, I don't know, means it will interact with whom and produce what. So that is the reason why it's not very promising for the BCC material. But if, as I said, the coincidence, so if there are certain coincidence, and in that coincidence process, if you can get approximately 30%, it has to be significant number, right? It has to break the connectivity. Otherwise, here and there certain sigma boundaries may not be so important for improving the bulk properties of the material. Please.
Like this J2 is essentially J3 only, right? Because 2 means the sigma will ultimately create another sigma. So J2.
No, not always, not always, not always, not always. No, there are certain, this question I think I had the answer, but currently I am not able to recollect. So there are certain constraints that is not that you will have J2, but J3 is not possible in that case. Okay.
But 2 sigma, when they meet, the third is automatically sigma, as you mentioned.
So currently no, I calculate those. I calculate and then I had the answer, but currently I am not able to recollect. I will tell you that why it is not anything. Huh? Yeah, sorry. Yes. Thank you very much. Yeah, thank you. So suppose sigma 33, okay, and sigma 13 interact. Not 33. Suppose 33 and anything which is beyond sigma 20, the third sigma is beyond sigma 29. Okay. For example, 13 and 3. Take these two examples. 13 and 3. What will be the third boundary? 39. It's a sigma, right? But then, should I consider it as J2 or J3? That triple junction? Yeah. Thank you. So.
Thank you.
So its boundary is sigma, but then the value is not fitting within the special boundary criteria.
Any more questions?
Yeah, please.
Hello, sir.
Yes.
Sir, you have mentioned about the thermomechanical treatments as one of the very well-known methods of getting this grain boundary engineering done. You have also mentioned about other processes also. Sir, in your opinion, how are the other processes, are they better, or do they have specific use cases for grain boundary engineering? Can you just little brief on that?
Yes, so thermomechanical processing advantages, almost most of the material undergoes thermomechanical processing, right? But having said that, you have other options like, nowadays additive manufacturing people are doing, right? So there you can have, your additive manufacturing parameters, one can fine tune, right? So additive manufacturing process also introduce some kind of strain, right? And then during cooling or during, annealing processes. So after additive manufacturing also you can do annealing, right? No? You should not thermomechanical process it, but you can anneal, right? So in that process, whatever strain was there in the material, that strain can play a role during annealing and can give this kind of grain boundary migration and introduces CSL boundaries. So that is the one of the direction of the research. You will find out some papers coming out recently, the grain boundary engineering through additive manufacturing or during additive manufacturing, right? So it's possible, right? Similarly, people have tried applying magnetic field. Like if you have a two phase, one is higher magnetic, properties compared to the second one. So if you apply magnetic field, the interface between the two fields, if they are of different phase, then we call it as interface, right? Interface between these two phases, what will happen? One phase will attract more compared to other phase, so they will migrate. So basically the process is you have to create some sorts of instability in the microstructure so that whether it is boundary or interface, they migrate, right? Please.
One more question from there.
why in BCC metals or materials that CSL is formed less in number?
So it's you know, the twin boundaries, like annealing twin boundaries. Why annealing twin boundaries are not formed in the BCC material, that will answer your question, right? So if you see the annealing twin, they don't form in the BCC material because they are not stable. So it's all about the energy criteria. Why twin are formed? Annealing twin are formed to, you know, to reduce the overall energy of the system, right? So we have to think from that point of view, because of the high stacking fold energy. So the twins are not stable in the BCC material. Yeah.
Yeah. So one more question. So how strict should we be with the deviation criteria? As we can see, the graph is telling us that this deviation will also decide the grain boundary energy associated with it.
No, the graph does not show you the deviation.
No, deviation, I means if you are going misorientation here and there,
Yeah.
so basically that GV energy is basically changing.
Obviously. No, what I am trying to say, you are right, your point is correct.
Yeah.
But this, can I go to the slide? Yeah. This curve, you know what my point is, this plot does not show you the, you know, deviation. This is the misorientation angle. This plot is, but you are absolutely correct. Suppose your deviation, although it is 8.67 degrees, but you know, again these are empirical, right? So normally, if it is a, so you know, there are two kind of twin boundaries typically, coherent twin boundaries and incoherent twin boundaries. So typically coherent twin boundaries will not so much deviation. Incoherent twin boundaries will it will show some deviation, but definitely not close to 8.67 now. So if your boundaries are showing deviation more than 4 degree, then definitely these are not a CSL boundary typically. Although, you know, criteria allows them to consider a CSL boundary. So more and more boundaries are oriented perfectly towards CSL is always better right now.
I have a question.
Sure.
This is green. Okay. It works?
Yeah.
Okay. So fractal dimension that you were talking about, especially if you're looking at something like stress corrosion where you need to have a connected path, is that a primary effect compared to the grain boundary energy, or is it a secondary effect? How important is fractal dimension?
So here fractal dimension tells about how well your random boundaries are connected, right? So suppose your mode of failure is intergranular, where the crack propagates to the grain boundaries. So if you have completely fragmented your grain boundary network, okay, so your fractal dimension will be very close to 1. So that means even my crack nucleates, it will not be able to propagate. So it's basically the fractal dimension does not consider anything about the plane, what is grain boundary plane, right? It only consider whether I have a continuously connected grain boundary network or not, random boundary network or not.
So continuously connected, but I was thinking of it more in terms of tortuosity of the
Yes.
problem, because the fractal dimension increases, right? So it's important as far as length, but as far as tortuosity, not so important.
Fractal dimension does not consider about tortuosity, it does not consider about the plane at all.
No, not the plane, but the path it considers, yeah?
But-
Because if you have a straight line
Yeah.
between A and B versus a jagged line, the fractal dimension is very different.
No, but that is the dimension of the crack you are talking about, or dimension of the boundaries you are talking about. Fractal dimension does not consider anything about the crack at all. It takes about the boundary. See, you know, like, you know, if I go to the slides. Oh, sorry, it is gone. Here, yeah. So from the random boundary map, we just extract the maximum boundary length, which is continuously connected, and based on that we apply some box algorithm is there. So based on the box algorithm, we found out what is the fractal dimension. So, it does not consider the nature of the crack at all, it only considers the boundary connectivity.
Yeah, but if that one in the bottom box was just a straight Y shape
Yeah.
instead of a squiggle shape,
Mm.
fractal dimension would be different.
Right. Mm.
So that's what I was thinking when I was thinking fractal dimension is how, I use the word tortuosity. How
Okay.
squiggly.
Okay.
That's what my question is it important?
So if I have a simply a Y shape, okay, and so in that case dimension will be different, I guess. In that case, if it is a straight boundary, and the value of the fractal dimension will be different, will be different, may not be, because finally the way we calculate, I don't have that slide, but actually what we do, we start with a higher box size. Okay, so this we divide it with we divide it. Suppose first we start with 4 boxes, so we divide this with 4 boxes, and I found out how many boxes out of these 4 boxes, how many boxes contain that random boundary. Okay, so in this case, suppose I have 4, so what will be the number of boxes that will have this boundary? All the 4. Here it may happen that maybe 2 boxes will have the boundary, another 2 boxes there is no boundary. So like then what we put, the box size is a function of number of boxes, and we keep on reducing the size of the box, and in that process, so if in this case you can see that the curve's straight line slope is higher, in this case slope is lower. So if I have, suppose instead of this, if I had a straight line one, I will have almost same dimension, it would not change.
Somebody said there was a glitch in the matrix.
Isn't it? So I don't think it will change, that value will remain same. So I don't think that it will take care about the tortuosity of the boundaries.
I think no more question, but finally I would like to comment something, but then you correct me if I am wrong. Okay, so I think that in many cases there are other factors also are very accountable, considering fatigue and fracture between boundaries. So in some cases the orientation difference between the 2 crystals in between which there is a boundary, if it is lower, then it leads to higher plasticity in the boundary, and in another cases there could be possibility where even though there is a CSL boundary present in between 2 different crystals, then if the orientation difference is too much, then it could generate a brittle crack sometimes. There are other possibilities, like for example a twin which is governed by twin boundaries in both the direction may contains lower dislocation density than the outside crystal, where the twin boundary can broaden by the strain induced boundary migration type of phenomena. In other case, there could be a possibility where the twin, which is governed by again CSL boundaries, have a higher dislocation density than the crystal outside, where it won't propagate further. Outside means it may not propagate. There could be another situation where because of the presence of multiple dislocations in the material, and when a dislocation in the matrix is moving and going towards a CSL boundary or a normal boundary and getting piled up there and leading to make another dislocation inside the that is also near the boundary in the twin domain, and this may happen to be sessile, or this may happen to be a gracile dislocation in some case, and then the property of the plasticity in the boundary and the formation of crack mechanism will change. So very complex.
Yeah, so obviously if suppose if you give more and more deformation, definitely the twin boundaries will lose their orientation, right, Namish orientation. So it may not remain as a CSL boundary.
Yes,
so
no, miss, I'm not saying that. Miss, I'm just saying that
that's obviously complicated.
Boundaries remain same, but piling up will definitely going to change it. Yes, yes. That is another case also. So many things, right?
Of course.
Very complicated metallurgy. Yes, of course. Quickly, yes. So it was very nice presentation, Sumantro.
Thank you.
And
Thank you very
I am
much.
very glad that you have come here and given such a good presentation. I would
pleasure.
really, I'm very grateful to you. I would request Professor Field to give you a small gift as a token of our affection for this presentation. I hope that the T-shirt fits you well. If not, please let me know.